Hello, friends. Welcome to the Snoozy Scientist, a quiet corner of the universe where science and wonder slow down just enough to guide you gently into rest. Tonight, we're traveling back billions of years to an age before oceans or mountains, before the sky ever stretched above the horizon, before Earth even existed. Back then, there was nothing but darkness and drifting dust, the scattered ashes of dead stars. And then, from that silence, something extraordinary began. Tiny grains collided and clung together. Pebbles grew into mountains. Mountains became worlds. And in a storm of collisions so violent it should have torn everything apart, the foundations of a planet began to form. Earth's story did not begin with peace. It began with chaos, with oceans of molten rock blasted into space, with newborn atmospheres stripped away by the sun's fierce winds, with whole worlds consumed and remade again and again. Scientists call this accretion, a slow, unstoppable process where dust becomes pebbles and pebbles become planets. For hundreds of millions of years, this fragile planet existed on the edge of annihilation, teetering between becoming a lifeless cinder and something far more remarkable. Yet somehow, from that brutal beginning, a sanctuary emerged, the only known world to cradle oceans, forests, and life itself. The evidence of that impossible origin is still all around us. It's written in ancient meteorites that fall from the sky, in the deep rocks beneath our feet that record time in the decay of atoms, and in the subtle chemistry etched into the oldest stones on Earth, traces of a time when there was no planet yet to bear them. But what really happened during those first impossible moments? How did something forged in such violence become a sanctuary so delicate, so beautiful, so alive? Tonight, we'll follow that story step by step from the chaos before creation to the fiery birth of a planet that, by all odds, should never have survived. If these calm journeys through deep time help you drift off or feed your curiosity, a gentle tap on the like button or a quiet subscribe helps more explorers find their way here too. And if you're still awake enough to type, I'd love to know where you're listening from tonight and what time it is where you are. It's always a joy to see how far this little sleepy corner of science travels. Now, take a slow breath, let your shoulders soften, and together, let's return to the moment everything began, the day Earth was born. Before there was Earth, or even a sun to warm the emptiness, there was darkness. The universe had already lived many lives by then. Countless stars had been born, shone for millions or even billions of years, and then died in spectacular fashion. Some ended their lives quietly, shrinking into faint embers. Others ended with unimaginable violence, collapsing and detonating as supernovae. These explosions were among the most powerful events in existence, bright enough to outshine entire galaxies for a brief moment in time. With each blast, they released the treasures forged in their fiery hearts, elements that did not exist in the early universe. Iron, silicon, oxygen, carbon were thrown out into the cold, expanding void. They were scattered far and wide, drifting across light years of space as tiny grains of stardust. These particles were unimaginably small, yet they carried within them the seeds of future worlds. Every rock that would one day make up mountains, every molecule that would form rivers and living cells, began as the ashes of stars that had long since burned out. For millions of years, this stardust floated silently through space. It gathered into thin clouds, then dispersed again, carried by the gravitational tides of the galaxy. There was no purpose to its drifting, no plan. It was only the slow dance of physics, the push and pull of mass and motion. And then, in one quiet corner of the Milky Way, the drifting clouds began to change. A shock wave from a nearby supernova rippled through a region filled with gas and dust. It was a gentle nudge by cosmic standards, but it was enough to disturb the delicate balance. The cloud began to collapse under its own gravity, pulling itself inward like water swirling into a whirlpool. Over time, far longer than the entire history of humanity, it flattened into a vast spinning disk. Scientists call this cloud the solar nebula, and within it, the story of Earth was waiting to begin. At the heart of the nebula, the pull of gravity grew stronger as more and more material gathered. Atoms were squeezed together until the pressure and heat were so intense that a new kind of fire began. Hydrogen atoms fused into helium, releasing immense amounts of energy. A new star was born. It shone for the first time about 4.5 billion years ago, and it is still shining today. This was our sun, young, bright, and fierce, its light pushing back the darkness that had surrounded it for eons. The birth of the sun changed everything. Its powerful gravity anchored the swirling disk, drawing most of the mass toward its center. The remaining gas and dust continued to circle, flattening into a thin pancake-shaped plane. Here, the building blocks of the planets began to gather. Tiny grains of rock and ice collided gently at first, sticking together through static electricity and molecular forces. Over thousands of years, they grew from dust motes into pebbles, from pebbles into boulders, and from boulders into bodies many kilometers across. This disk was a chaotic, violent place, but it was also a nursery, a place of creation. Every planet in our solar system, from the smallest chunk of rock to the largest gas giant, took shape within this swirling band of material. Close to the sun, where it was too warm for ice to survive, rocky worlds like Mercury, Venus, Earth, and Mars began to form. Farther out, beyond a line where the temperature dropped low enough for ice to persist, the giant planets gathered enormous amounts of frozen gas and dust, growing into titans like Jupiter and Saturn. But it all began with that first generation of stars. Without their fiery deaths, there would have been no heavy elements to build solid planets. Without the supernova shock that triggered the nebula's collapse, our sun might never have formed. And without the sun's ignition, the solar system would have remained a cloud of drifting dust forever. The atoms in your bones, the oxygen in your breath, even the silicone that makes up the screen you are reading this on, all trace their origins back to those long-dead stars. Every heartbeat, every leaf, every wave on every ocean is made of ancient stardust. The story of Earth does not begin with Earth itself. It begins in the cores of stars that lived and died long before our planet was ever born, in a universe that was already old when the sun first lit the sky. And from their ashes, a new story began to take shape, one that would one day become home. In the silence that followed the sun's ignition, the swirling disk of gas and dust around it was far from calm. It was a restless, crowded place, filled with fragments born from the same collapsing nebula that had created the star itself. Gravity, patient and relentless, began to work its quiet magic here. At first, it acted on the smallest of scales. Tiny grains of stardust, each lighter than a breath, collided gently within the rotating disk. Most of these encounters ended without change, but occasionally two grains would cling together, bound by the faintest electrostatic pull. These fragile beginnings were the first steps towards something far greater. Over thousands and then millions of years, these microscopic specks built upon one another. Grains grew into pebbles, pebbles into stones, and stones into boulders. But this was no smooth or graceful construction. The early solar system was a maelstrom, a turbulent arena where countless particles raced around the sun at immense speeds. Collisions were constant and often catastrophic. Some clumps stuck together and grew larger, while others shattered apart in violent impacts, scattering debris back into the disk. It was a cosmic foundry without order or design, where destruction and creation happened side by side. As these fragments grew, gravity began to tip the balance. Larger objects exerted stronger pulls, attracting smaller ones and accelerating their own growth. Boulders became bodies kilometers across, and these larger chunks, called planetesimals, were the pioneers of planetary construction. They moved through the disk like magnets sweeping through a sea of dust, gathering material into their orbit. But success was rare. For every planetesimal that grew, countless others were obliterated in collisions or flung into distant regions of space. The path from dust to planet was not a steady climb, but a brutal contest, with most competitors destroyed before they ever had a chance to evolve. The physics of this process followed a self reinforcing rule. The more massive an object became, the more quickly it could grow. A small planetesimal might take millions of years to double its size, but once it crossed a certain threshold, its growth accelerated dramatically. It pulled in material from farther away, its gravitational influence expanding like ripples in a pond. With each new collision, it became heavier, and with greater mass came even stronger gravity. This feedback loop turned modest planetesimals into dominant forces, setting the stage for the birth of protoplanets. Yet the young solar system remained dangerous and unpredictable. Orbits crossed and shifted chaotically, leading to spectacular collisions that could destroy worlds in progress in moments. Some planetesimals were hurled into the sun, vaporized before they could grow further. Others were ejected entirely, exiled into deep space to wander among the stars. The solar system became littered with these failed worlds, silent reminders of how precarious planetary birth truly was. Only a handful of bodies survived the constant bombardment, and those that did grew larger and more powerful with every passing epoch. Among the survivors, the most massive planetesimals cleared their orbital neighborhoods, sweeping up nearby material in a process known as accretion. They became protoplanets, embryonic worlds with enough gravity to dominate their surroundings and shape their own evolution. These young planets continued to collide, but now the impacts were fewer and far more dramatic. When two protoplanets met, the results could be catastrophic, merging their masses into a single larger world, or shattering them into fragments that would reassemble over time. It was within this chaotic environment that the earliest version of Earth began to form. Its orbit lay in a region of space neither too hot nor too cold, where silicate rock could condense and remain stable. Here it grew steadily as it swept through the thinning disk, pulling in the last remnants of surrounding debris. Each collision added not just mass but energy, heating the growing planet from the inside out. Its surface was violent and unstable, a landscape shaped by continuous impacts and internal pressures, while its interior compacted under immense gravitational force, becoming denser and hotter with time. As the solar system aged, the once dense disk of gas and dust thinned out. Intense radiation from the young sun blew away much of the lighter material, leaving behind a more orderly arrangement of objects. The largest protoplanets carved out stable orbits, each dominating its own region of space. The frenzy of constant collisions gave way to a quieter, more deliberate process of growth. Smaller fragments were now drawn in gently rather than smashed apart, and the architecture of the solar system began to resemble the one we know today. What remained was a small collection of survivors, the last products of a brutal and unforgiving selection process. Countless planetesimals had perished, scattered, or been absorbed, but the few that endured would become the worlds we now see orbiting the sun. Among them was the young Earth, still unrecognizable and chaotic, but growing stronger with every passing moment. It had no oceans, no atmosphere, no continents, and no life. Yet deep within this storm of collisions and chaos, the foundation of a living world was being laid, one impact at a time. The violent birth of planets was not a single event, but a drawn out struggle that shaped the destiny of every world in the solar system. Gravity had transformed clouds of stardust into solid worlds, setting in motion a chain of events that would continue for billions of years. For Earth, the story was just beginning. What followed would be even more dramatic: colossal collisions, planetary mergers, and transformations that would shape the surface, interior, and future of the only world we know to harbor life. In the silence of space, one of the growing worlds in the young solar system was beginning to pull ahead of the rest. It was not yet Earth as we know it. It had no continents, no oceans, no air to breathe, and certainly no life. But it was larger and heavier than most of its neighbors, and with each collision it swallowed, it grew stronger. Its gravity deepened, drawing in more material, and with every new impact, its body changed. What had once been a scattered collection of rock and dust was becoming something far more substantial, a newborn planet in the making. It was a violent kind of growth. Enormous chunks of debris, some the size of mountains and others the size of small worlds, crashed into its surface with incredible force. Each impact released more energy than all the volcanoes on modern Earth combined. The collisions were not rare events that happened once in a while. They were constant, happening again and again as the young world swept its path clean. With every strike, heat poured into its interior, building a temperature so high that the surface never had a chance to cool. Deep within, another source of energy was working in silence. As the growing planet collected more mass, it trapped radioactive elements left behind from ancient stars. These unstable materials released heat as they decayed, and together with the energy from constant impacts, they turned the entire body into a molten sea. From its core to its outermost layers, this young world was a churning sphere of liquid rock, glowing faintly red against the darkness of space. It was not solid, it was not calm, it was an ocean of magma, reshaping itself from the inside out. On the surface, there were no stable features, no mountains or plains, no familiar landmarks. Rivers of molten rock flowed like slow fire, colliding and merging in great glowing currents. Waves of heat shimmered above the surface, and fountains of vapor burst upward where impacts struck hardest. Nothing stayed the same for long. Each collision rearranged the landscape. Each moment remade the surface anew. It was a place of relentless change, a planet still deciding what it was going to be. Even its earliest attempts at forming an atmosphere were swept away before they could take hold. As the molten world released gases into space, carbon dioxide, water vapor, and other compounds from deep within, they barely had time to gather before they were stripped away by the young sun. The solar wind, a stream of charged particles flowing outward from the newborn star, blew with incredible strength. It blasted the lightest gases into space and tore at anything that tried to cling to the planet. Again and again, thin veils of atmosphere formed, only to be lost to the void. The planet remained naked and exposed, its fiery skin laid bare to the cold emptiness around it. It was a harsh and unrecognizable place. There was no blue sky overhead, no soft clouds drifting in sunlight. The glow that surrounded this young world came from within, not from without. It burned with the energy of its own creation, its surface lit by the molten rock beneath. To anyone watching from afar, it would have looked like a glowing ember floating through the dark, a red-hot sphere slowly cooling from the inside, but never quite reaching the point of rest. Beneath that molten surface, heavy elements like iron and nickel were sinking toward the center, forming a dense core. Lighter materials floated upward, layering themselves into a primitive mantle and crust. This separation would shape the planet's structure for the rest of its life, creating the foundations of a dynamic interior that would one day move continents and build mountains. But at this early stage, everything was still fluid and in flux. The young world had no stable surface, no permanent shape. It was a place still becoming itself. Even the light from the sun, though steady and bright, could do little to tame this fiery world. The energy pouring from within was far greater than anything the sunlight could offer. And so the planet glowed in solitude, a nameless body circling its star, its surface forever remade by impacts and heat. It was not yet Earth. It had no oceans to cradle life and no air to carry sound. It had no weather, no seasons, no landscape to speak of. But deep inside this molten sphere, the story of Earth was already taking shape. Its layers were forming, its structure was solidifying, and its gravity was beginning to clear a path through the crowded solar system. The planet that wasn't yet Earth was still raw and chaotic, still more fire than stone, but it was there, a seed of something far greater, waiting for the next chapter of its story to unfold. In the quiet dark of the early solar system, a silent wanderer was drifting through space. It was not a comet, nor a wayward asteroid, but a young world in its own right, a planet about the size of Mars. Scientists would one day give it a name, Theia. Like Earth, Theia had formed from the same swirling disk of gas and dust. It had followed its own path around the newborn sun, growing larger with every collision, shaping itself as gravity pulled it into a sphere. For millions of years, its journey had been calm and uneventful, but its orbit was bringing it ever closer to the molten young Earth. The two worlds were locked in a slow motion dance, and their paths were destined to cross. The collision that followed was unlike anything the solar system had seen before or since. Theia did not simply graze Earth and continue on its way. It struck head on, an impact so immense that it released more energy than billions of nuclear bombs exploding at once. The young Earth shuddered under the force, its crust vaporized in an instant. Mountains of molten rock were hurled into space. Vast portions of both planets' mantles were torn away, ripped apart by the violence of the collision. For a brief moment, neither world existed in any recognizable form. They were clouds of incandescent debris, glowing like liquid fire, spreading out into space. What happened next was not destruction, but transformation. Much of the shattered material fell back to Earth, merging with what remained of its body. But a significant portion stayed in orbit, circling the ruined planet in a chaotic ring of molten rock and dust. Within that orbit, gravity began its slow, patient work once again. Pieces collided and clumped together, forming larger and larger fragments until, at last, a new celestial body took shape. From the wreckage of two worlds, a third was born. That body would become the moon. It was smaller than either Earth or Theia had been, but it was massive enough to change everything. Over time, the molten sphere that was now Earth cooled enough for its surface to solidify once again. The moon orbited closer than it does today, looming enormous in the young planet's sky. It tugged at Earth's molten surface with its gravity, pulling the oceans of magma into bulges, subtly reshaping the planet's spin and slowing its rapid rotation. The moon's influence did not stop there. In the chaotic early solar system, planets often wobbled unpredictably, tipping and tilting as impacts threw them off balance. Without the moon, Earth's axis might have shifted wildly over time, flipping the poles or plunging the planet into chaotic climate swings. But the new satellite acted like a stabilizing hand. Its steady gravitational pull anchored Earth's tilt at a gentle angle of about 23.5 degrees. This tilt would become one of the defining features of the planet's future, governing the rhythm of its seasons and the balance of its climate. Tides were another gift from this cosmic collision. The moon's pull on Earth's surface would one day draw the waters of its oceans back and forth in a slow, eternal dance. These tides would shape coastlines, stir nutrients, and influence the cycles of life itself. They would become a heartbeat for the planet, a subtle but powerful force that guided the rise and fall of ecosystems. Thea's collision also left its mark deep beneath Earth's surface. Some scientists believe that parts of Thea's mantle were absorbed into Earth's interior and still remain there, buried far below the crust in strange, dense regions that influence how heat moves through the planet. Others think the collision's energy might have jump started Earth's internal engine, setting the stage for the magnetic field that would one day protect its atmosphere from the solar wind. What began as an act of near total destruction ended up shaping the planet's destiny. Without Theia, Earth might have spun too fast, wobbled too wildly, or never formed a large moon at all. It might have remained a chaotic, unstable world, incapable of nurturing the delicate balance that life would one day require. The moon's presence became a constant companion in Earth's long story. Night after night, it watched silently over the cooling planet, pulling gently at its surface, anchoring its tilt, guiding its tides. It was a reminder of the violence that had forged it, and a symbol of the strange paradox of creation that sometimes only through catastrophe can a world truly take shape. The collision between Earth and Theia was not an ending, it was a turning point. The planet that had once been just another molten sphere was now something more, a world with a moon, a stable axis, and the beginnings of the conditions that would one day make life possible. In the silence after the impact, amid the glow of a newborn satellite, Earth's future had begun to unfold. In the aftermath of the colossal collision with Theia, the young Earth no longer resembled a planet at all. What had once been a growing sphere of rock was now a blazing, molten world. The force of the impact had shattered crust and mantle, melted vast amounts of material, and hurled countless fragments into space. What remained was a churning globe of liquid stone, glowing red and orange like a star that had not quite managed to ignite. Temperatures soared above 2000 degrees Celsius. At such heat, solid rock behaved like water, flowing and swirling in slow, hypnotic currents. Waves of molten silicate rolled across the planet's surface, rising and falling in fiery tides driven by the immense heat below. From above, the Earth would have looked like a glowing ember suspended in the darkness of space, its surface constantly reshaped by convection and violent eruptions. There were no continents, no mountains, and no oceans of water. The planet was a restless sea of magma stretching from horizon to horizon. The air, if it could be called that, was nothing like the atmosphere we know today. Instead of blue skies and drifting clouds, there was only a heavy, toxic veil of vapor. Superheated gases boiled off the surface and rose into space, forming a temporary atmosphere of silicates, carbon dioxide, and metal-rich steam. The pressure near the surface was immense, and the air shimmered with heat, glowing faintly from the energy radiating below. Any water delivered by early comets or planetesimals was instantly vaporized, swept up into the violent, swirling sky. Deep beneath that fiery surface, the planet was alive with movement. The colossal impact had not only melted the outer layers, but also superheated the interior. Vast quantities of radioactive elements, inherited from the debris of long-dead stars, released their energy through decay, keeping the young Earth hot from the inside out. Combined with the heat from countless collisions that followed, this energy drove powerful convection currents deep within the mantle. Molten rock rose and fell in slow, majestic cycles, carrying heat toward the surface and pulling cooler material down into the depths. These cycles, though invisible from above, were already shaping the structure of Earth's interior. The boundary between surface and space was a scene of ceaseless violence. Plumes of lava erupted upward from deep fissures, splattering the landscape with fountains of molten rock. Gases burst free in explosive jets, releasing clouds of silicate vapor into the sky. Each eruption reshaped the planet's appearance, building new features that were quickly swallowed again by the restless magma sea. Occasionally, fragments of rock ejected by the Theia collision fell back to Earth, crashing into the molten surface with enough force to send glowing sprays of material hundreds of kilometers into the air. Despite the chaos, this was a crucial stage in Earth's development. As the magma ocean churned and cooled, heavier elements like iron and nickel began to sink toward the center, forming the dense metallic core. Lighter materials floated upward, eventually giving rise to the mantle and crust. This process, known as differentiation, laid the foundations for the layered planet we inhabit today. Deep within the interior, the growing core began to spin, setting the stage for the magnetic field that would one day shield the planet from the solar wind. Above, the atmosphere continued to evolve. With each eruption, volcanic gases billowed into the sky, adding layers of carbon dioxide, sulfur, and steam to the dense, suffocating envelope. Most of this early atmosphere was temporary. The relentless solar wind stripped away lighter molecules, scattering them into space. Others were trapped again in the molten surface or dissolved into the magma itself. It would take millions of years before a more stable sky could form, but the seeds of it were already being sown. On the surface, the transition from molten chaos to solid ground was painfully slow. As the Earth radiated its heat into space, thin crusts of rock began to form, drifting like fragile rafts atop the fiery ocean. Many were short-lived, breaking apart and sinking back into the molten depths. Over time, however, these patches grew more stable, clinging to the surface for longer periods before being consumed. The first hints of a planetary crust were beginning to appear, though the Earth remained a world dominated by fire. Seen from afar, the young planet was both terrifying and beautiful. It pulsed with energy, glowing with the light of its own creation. It was a world in the making, forged in the heat of collisions and reshaped by forces that had been set in motion billions of years before. The seething magma ocean was not a sign of destruction but of transformation, a necessary step in the long journey from chaos to complexity. In this violent and inhospitable state, the Earth was still far from becoming the cradle of life it would one day be. Yet every surge of molten rock, every plume of gas, and every flicker of heat was part of a process that was slowly, almost imperceptibly, building a stable foundation. The planet was not yet ready to host oceans or continents, but beneath its glowing surface, the pieces of that future were already beginning to fall into place. The world that had once been wrapped in molten rock was beginning to cool and harden, but calm was still a distant dream. The colossal collision that had created the moon was not the final act in Earth's violent youth, only a prelude to something even more chaotic. Around the young sun, the solar system remained a place of turmoil and debris. Billions of fragments, leftovers from planet formation, still hurtled through space. Some were grains of dust, others were mountains adrift among the stars, and a few were the size of small planets. Earth, now larger and more massive than ever, became an irresistible gravitational target. Its growing pull swept these wandering bodies inward, but every piece that fell came at a terrible cost. Scientists call this era the bombardment years, and the name is no exaggeration. The impacts were constant, relentless, and unimaginably powerful. Some arrived as daily showers of small rocks that pelted the surface like cosmic hail. Others came as catastrophic collisions that struck with energies beyond anything Earth would experience again. Even a body only a few kilometers across could release the power of millions of modern nuclear weapons on impact. Larger objects, tens or even hundreds of kilometers wide, unleashed enough force to vaporize enormous regions of crust and shake the entire planet to its core. When these colossal bodies struck, they did not simply carve craters, they exploded with such intensity that entire portions of Earth's surface were hurled into space, and the rock beneath the point of impact was instantly transformed into vapor. Gigantic plumes of molten debris shot outward, glowing arcs that rained back down as incandescent storms of fire. The heat from these impacts could melt vast regions of the crust, undoing millions of years of slow cooling in moments. Even as the planet tried to solidify, it was repeatedly thrown back into turmoil. The scale of this bombardment is difficult to comprehend. Scientists estimate that in this era, Earth was struck by objects large enough to alter its surface every few thousand years, and smaller impacts happened almost daily. Some collisions were so immense they may have tilted Earth's axis slightly, changing the angle at which sunlight struck the planet and setting the stage for the climates that would come much later. Others blasted so much material into space that some of it never returned, lost forever to the void. Every impact reshaped the planet's story, writing it in shock waves, molten rock, and dust. The skies above mirrored the violence below. Each collision hurled enormous amounts of vaporized rock, gas, and debris into the atmosphere. Much of it escaped Earth's gravity entirely, scattering into space, but the rest formed choking clouds that blanketed the sky and blocked the sunlight. Periods of darkness followed as ash and molten droplets fell back to the surface in fiery rains. Over and over, the cycle repeated: impact, vaporization, cooling, and then another impact. While this was primarily an age of destruction, not everything about it was ruin. Many of the bodies striking Earth contained volatile substances locked deep within their minerals, including water and gases. Although the amounts delivered during this stage were relatively small, they hinted at the chemical richness that would come later. These materials would not yet transform the planet, but they were early signals of changes still to unfold. The effects of these collisions extended deep into the planet's interior. The repeated impacts stirred and heated Earth's mantle, keeping it in motion and slowing the process of crust formation. In some regions, the surface melted entirely, forming vast lava plains that stretched for hundreds of kilometers. The energy of each impact rippled through the young planet, driving convection currents and accelerating the separation of materials by density. Heavy elements sank deeper toward the core, while lighter silicates floated upward, shaping the structure of Earth from within. Even the moon, Earth's silent companion, bore witness to this chaos. Its own surface was scarred and cratered by the same relentless bombardment. Unlike Earth, the moon lacked tectonic activity and erosion, so its craters remained as permanent records of this violent chapter. They are still visible today, frozen snapshots of an era that Earth's more active geology has long since erased. As millions of years passed, the storm began to ease. The solar system gradually cleared itself of debris. Some planetesimals were swallowed by growing planets, some were ejected into distant orbits, and many shattered into smaller fragments that eventually burned up or merged with larger bodies. The impacts continued, but their frequency and intensity diminished with time. Earth was no longer constantly battered by titanic collisions, though smaller impacts would remain a fact of life for billions of years. The rain of stone left Earth forever changed. Its crust was scarred and reworked, its interior stirred and heated, and its orbit subtly shaped by countless gravitational encounters. The planet that emerged from this storm was no longer the same young world it had been before. It was tougher, denser, and more stable, forged in the furnace of collisions. The bombardment had been an era of chaos and destruction, but it was also a relentless force of creation, sculpting the planet into a body capable of evolving into something far greater than a lifeless sphere of rock. The violence was far from over, but Earth had survived, and in surviving, it had been transformed. The surface of the young Earth was still a place of chaos. It was shaken by deep internal heat, scarred by constant impacts, and covered in rivers and lakes of molten rock. But above that restless surface, a quieter struggle was taking place. It was the story of a thin, fleeting veil of gases that formed and vanished again and again. This was Earth's first atmosphere, a fragile skin of air that was never meant to last. In the beginning, there was nothing at all. The space around Earth was empty, and the naked surface lay exposed to the raw radiation of the young sun. But the same violent forces that shaped the ground beneath also began shaping the sky above. When enormous impacts slammed into the surface, they vaporized vast amounts of rock, launching clouds of silicate vapor into space. Volcanic eruptions, driven by intense heat trapped inside the planet, spewed plumes of gas upward. These early outbursts contained carbon dioxide, sulfur dioxide, water vapor, nitrogen, and traces of other chemicals once locked deep within the mantle. Together, this mixture of vaporized rock and volcanic gases created Earth's first primitive atmosphere. It was nothing like the air we know today. It was thick and heavy, filled with dust and metallic particles, and it glowed a dull orange beneath the harsh light of the sun. Temperatures near the surface were so high that droplets of molten rock condensed briefly in the sky before falling back down and evaporating again. The pressure was immense, and the air itself was dense enough to behave almost like a fluid. This was a silicate atmosphere, born directly from fire and stone, but this new layer of gas was fragile. The sun in those early days was far more active than it is now, throwing out powerful bursts of radiation and streams of charged particles. This solar wind slammed into Earth's upper atmosphere, stripping it away particle by particle. Without a strong magnetic field to deflect it, the atmosphere could not hold on. Much of it was swept into space, leaving the surface exposed once again to the emptiness beyond. The damage did not come only from above. The early solar system was still filled with leftover debris, and impacts continued to batter Earth with relentless force. Each collision peeled away parts of the atmosphere, blasting gas into space and undoing whatever progress had been made. In some cases, impacts were powerful enough to wipe the atmosphere out almost entirely, forcing the planet to start over from nothing. This was the reality of Earth's earliest sky, a constant cycle of creation and destruction where every gain was followed by loss. Despite this, the planet refused to remain bare. Its interior was still alive with immense heat, and that heat pushed upward in the form of volcanic eruptions and continuous outgassing. Carbon dioxide, nitrogen, sulfur, and steam poured from fissures and vents, rising high above the surface and forming new layers of atmosphere. Each eruption rebuilt what had been lost, though often only for a short time. The process was slow and repetitive, but over millions of years, it created a pattern. Impacts and solar winds would strip the sky away, and the earth would build it again from within. This balance between loss and replenishment shaped the atmosphere's composition. Lighter gases, like hydrogen and helium, were easily lost to space, leaving behind heavier molecules that clung more tightly to the planet. Carbon dioxide became a dominant component, forming a dense, heat trapping blanket. Nitrogen, heavier still, began to accumulate. Water vapor, though still present, could not yet form rain. The surface remained far too hot for condensation, and the steam lingered as part of the volatile mix. The violence from space slowly began to ease as time passed. Fewer planetesimals remained to collide with Earth, and the impacts became less frequent and less intense. At the same time, changes deep inside the planet were working in its favor. As iron and nickel settled toward the center, they formed a metallic core. Movement within this molten heart generated a magnetic field, an invisible shield that stretched far into space. This new magnetosphere began deflecting much of the solar wind, preventing it from stripping away the atmosphere as easily as before. It was not a perfect defense, but it was the beginning of stability. Even with this protection, the atmosphere was still far from secure. It remained hot and toxic, and its composition shifted with every eruption or impact. Periods of thinning alternated with periods of thickening, and the boundary between air and space was constantly in flux. Yet, compared to the fragile silicate clouds of the earliest days, this new atmosphere was starting to endure. It lasted longer between disruptions and contained gases that would eventually influence the planet's chemistry in profound ways. This was not yet the breathable sky of the future. It was still hostile, still volatile, and still changing, but it was a sign that the planet was maturing. For the first time, a layer of gas had begun to linger, even if only briefly. It was a fragile shield born of destruction and renewal, torn away by the sun and rebuilt from the depths again and again. And though it could not yet support rain, weather, or life, it was laying the groundwork for the transformations that would follow. This atmosphere, tenuous as it was, marked the beginning of Earth's long journey toward becoming a living world. When the planet finally cooled enough, the long age of fire and impact gave way to something entirely new. The surface that had once glowed with liquid rock now lay beneath a heavy sky, and the air, still dense and hot, carried more water vapor than it could hold. After millions of years of relentless heat, a simple shift began that would change the world forever. Steam started to condense, and the first rain began to fall. At first, these early droplets never reached the ground. They vanished the instant they touched the still searing surface, flashing back into vapor in tiny bursts of steam. But as the crust cooled and hardened, more of them survived their descent. They splattered against hot rock and hissed as they boiled away, and then, slowly, they began to linger. The surface no longer burned them instantly, and water, for the first time in Earth's history, could remain. Then the rains came in earnest. They were not like any storm we know today. This was not a passing weather system or a seasonal downpour. It was a continuous, planet-wide deluge that lasted for thousands upon thousands of years. Water fell without pause, drawn from the vast reservoir of steam that had built up in the atmosphere. The sound of it would have been relentless, a constant drumming against the surface, a rhythm that did not stop. The clouds above were so thick that sunlight could barely reach the ground, and the air below was heavy and dim. This rainfall was more than weather. It was a geological force, and it reshaped the young planet in profound ways. Rivers formed where none had ever existed. They cut through cooling rock, carving valleys and channels into the surface. Torrents of water swept loose debris into basins and craters, filling lowlands and smoothing jagged landscapes that had been forged by fire. Dust and ash from ancient eruptions were carried into deep depressions where they settled beneath the rising water. Lightning cracked through the thick clouds, igniting bursts of energy in the atmosphere and adding new chemistry to the young world. Every strike drove reactions in the gases above, forming new compounds that mixed with the rain and washed into the surface below. The water that pooled on the ground was unlike anything familiar today. It was dark, dense, and acidic, carrying with it dissolved minerals and volatile chemicals drawn from both the air and the rocks it touched. These waters did not yet resemble the blue oceans of the modern Earth, but they were the beginnings of them. As the rains continued, the balance of the atmosphere began to shift. With so much steam condensed into liquid and falling to the ground, the air grew thinner and cooler. Greenhouse gases that had once trapped immense heat now found less water vapor to amplify their effect. The surface cooled further, allowing even more condensation, which in turn led to even heavier rain. A powerful feedback loop had begun, one that transformed the surface from a barren, glowing wasteland into a world where water dominated the landscape. The transformation extended far beneath the surface. Water seeping into cracks and fractures cooled the rocks below, altering their structure and triggering chemical changes deep underground. These interactions formed new minerals and locked others into the crust, changing its composition. At the same time, dissolved minerals from weathered rock poured into the growing bodies of water, enriching them with elements that would later play a crucial role in the chemistry of life. Over time, the low-lying regions of the planet filled completely. Basins carved by ancient impacts became enormous lakes. Craters turned into inland seas. Valleys became riverbeds, and entire regions disappeared beneath rising waters. Gradually, these scattered pools merged, forming vast interconnected bodies of water. The first oceans of Earth had begun to take shape. These oceans were unlike those we know today. They were acidic and dark, thick with dissolved metals and minerals, and churning with chemical reactions. Yet they were also dynamic and active, constantly shaped by the interplay of water, rock, and atmosphere. Waves battered newly formed coastlines, eroding cliffs, and carrying sediment far from its source. Rain continued to fall, adding volume and driving erosion further. Rivers carved deeper into the crust, and over time, their sediments built new layers on the ocean floor. The presence of liquid water also began to influence the atmosphere itself. Water vapor levels dropped significantly as much of it condensed and fell, and the temperature at the surface stabilized at lower levels. Clouds grew thinner and more transient, allowing more sunlight to penetrate and warming the surface just enough to maintain liquid oceans. This new balance between air, water, and rock created a feedback system that would continue to evolve for billions of years. The world that emerged from this age of rain was unrecognizable from what had come before. The era of relentless bombardment and searing heat had ended, and in its place was a planet wrapped in water. Vast oceans stretched across its surface, their waves breaking against volcanic islands and newly formed coastlines. Valleys and basins were carved deeper with every passing century. The land and sea interacted in ways that would shape the planet's future, driving cycles of erosion, sedimentation, and chemistry that laid the groundwork for life. The rain did not merely cool the earth, it transformed it. In the space of a geological moment, a world once dominated by fire and stone became a world defined by liquid water. Oceans now covered much of its surface, altering its atmosphere, reshaping its crust, and setting the stage for everything that would follow. Deep beneath the surface of the young Earth, hidden far below the oceans of water and the layers of solidifying rock, something extraordinary was beginning to take shape. The planet's interior, still hot from countless collisions, and the slow decay of radioactive elements, was alive with movement. It was not quiet in those depths. Heat churned the heavy elements downward and lighter ones upward, stirring the molten material into slow, powerful currents. And within this restless interior, the most important transformation in Earth's history was unfolding, the birth of its magnetic heart. When Earth first formed, its composition was a chaotic mix of rock, metal, and debris from older stars. But as the planet grew hotter, these materials began to separate based on their density. The heaviest elements, primarily iron and nickel, sank toward the center, drawn by gravity's relentless pull. Lighter silicates and minerals rose toward the surface, forming the mantle and crust. Over time, the descent of metals created a dense, molten core at the planet's center. This was differentiation, a process that reshaped the structure of Earth from the inside out. At first, the core was entirely liquid, a swirling sea of molten iron and nickel heated to thousands of degrees. The immense pressure at the planet's center kept it from solidifying, even as the rest of the interior slowly cooled. But the process of cooling continued, and eventually, the very center of the core began to crystallize. A small, solid inner core formed, surrounded by a vast liquid outer core that remained in constant motion. It was this motion that would soon change everything. The liquid iron in Earth's outer core behaved like a conductor, carrying electric currents as it moved. Driven by heat from radioactive decay and the slow cooling of the planet, these currents formed convection cells that twisted and churned deep beneath the surface. As the molten metal shifted and flowed, it generated complex patterns of electrical charge, and wherever electric currents flow, magnetic fields follow. What began as a subtle effect soon grew into something powerful. The movement of molten iron acted like a planetary dynamo, creating invisible lines of force that stretched outward from the core and wrapped around the planet. Earth's first magnetic field had been born. It was weak at first, fluctuating and unstable, but over time it strengthened and stabilized as convection patterns deepened, and the core's rotation helped align the magnetic forces into a coherent field. This new shield reached far beyond the surface, extending thousands of kilometers into space. It formed an invisible barrier around Earth, bending and deflecting the charged particles that streamed outward from the sun. Before the magnetic field existed, the solar wind had battered the planet directly, stripping away much of its early atmosphere and sweeping lighter molecules into the void. But now, those particles were forced to flow around the magnetic field, leaving the atmosphere far more protected than before. This protection would become one of Earth's most critical features. The magnetic field did more than guard the air. It prevented the relentless solar wind from eroding the water vapor and gases that were slowly accumulating. It shielded the surface from streams of charged particles that could have broken apart molecules and sterilized the environment. Without it, Earth might have followed the fate of Mars, whose weak magnetic field allowed its once thick atmosphere to escape into space, leaving it cold and barren. The presence of a magnetic field also helped shape the planet's climate and surface conditions. By preserving the atmosphere, it allowed greenhouse gases to trap heat and keep temperatures within a range that liquid water could survive. It protected the delicate balance that was forming between the air, the oceans, and the rocky surface below, and in doing so, it laid the foundation for the long chain of events that would one day lead to life. From space, the influence of the magnetic field was invisible, but its effects were everywhere. High above the planet, charged particles trapped within the field's lines of force formed belts of radiation. Occasionally, some of these particles spiraled down into the upper atmosphere, colliding with gas molecules and releasing energy as shimmering curtains of light. These were the first auroras, silent displays that revealed the unseen shield at work. The magnetic field was not static. It shifted and fluctuated as the convection patterns within the core evolved. Sometimes it weakened, and at other times it grew stronger. Over geological time, it even reversed direction, flipping the positions of magnetic north and south. But through all these changes, it remained a vital part of Earth's identity, a protective bubble that allowed the atmosphere to grow thicker and the surface to become more stable. As the young planet spun beneath its new magnetic shield, it was no longer as vulnerable to the forces that had once threatened it. The solar wind still streamed outward from the sun, but now it was deflected and tamed. The atmosphere, no longer stripped away as quickly, could build and change. Water vapor could remain in the sky long enough to condense, and gases could accumulate to form layers that would shape weather and climate. Deep below, the molten heart of the planet continued its ceaseless motion, driving the dynamo that sustained the shield. It was a silent process, unfolding far beyond the reach of sight, yet it was one of the most important events in Earth's long history. With the awakening of its magnetic heart, the planet had gained a powerful tool for survival, one that would make everything that followed possible. High above the newborn Earth, a silent companion circled through the dark. It had been born from catastrophe, forged in the fiery collision between Earth and another young world. Now, as the planet continued to cool and evolve, the moon remained, pale and watchful, its presence subtle yet profoundly powerful. It was far more than a glowing sphere in the night sky. Its influence reached deep into the mechanics of Earth itself, shaping the conditions that would one day allow life to flourish. At first, the moon was much closer to Earth than it is now. It loomed large, filling a vast portion of the sky, its surface still hot from its violent birth. Over millions of years, it cooled and hardened, becoming the cratered satellite we know today. But its closeness meant its gravitational pull was far stronger then than it is now. That pull reached deep into Earth, tugging on its oceans, its crust, and even its spin. One of the moon's most important roles was stabilizing Earth's axial tilt. As the young planet spun on its axis, its tilt determined the rhythm of its seasons and the distribution of sunlight across its surface. Without the moon, that tilt would have been unstable, wobbling unpredictably under the gravitational influence of the sun and other planets. Over long timescales, Earth's axis might have shifted dramatically, causing wild swings in climate. Ice sheets could have crept toward the equator in one era, then retreated toward the poles in another, creating an environment too unstable for complex life to ever emerge. But the moon's gravity acted as a stabilizing anchor. It tugged gently on Earth's equatorial bulge, resisting changes in the tilt and locking it into a relatively narrow range. The planet's axis still shifted slightly over long cycles, but the changes were slow and predictable. This stability allowed climates to remain consistent over millions of years, giving ecosystems time to adapt and evolve. It ensured that seasons would follow a steady pattern and that the energy from the sun would be distributed in a way that supported the development of stable environments. The moon's pull also shaped Earth's rotation. In the planet's earliest days, it spun rapidly, completing a full rotation in only a few hours. The days were short, and the winds howled across its surface at incredible speeds. But the moon's gravity began to act as a brake. Its pull on Earth's mass created tidal bulges in the oceans and crust, slightly deforming the planet's shape. As Earth rotated, these bulges were dragged forward, and the gravitational interaction between them and the moon siphoned off the planet's rotational energy. Slowly, Earth's spin began to slow, What had once been days only a few hours long stretched to 6 hours, then 8, then 12, and eventually the 24-hour cycle we know today. The slowing rotation changed many aspects of the planet. Winds grew calmer, weather patterns shifted, and the daily cycle of light and darkness lengthened, creating conditions that would influence everything from the behavior of tides to the pace of biological rhythms once life emerged. Tides were one of the most visible effects of the moon's influence. Even in those early days, when oceans were young and alien, the moon's gravitational pull caused the waters to rise and fall in great rhythmic movements. At first, with the moon so close, these tides were immense, far larger than those we see today. They surged across coastlines, flooding low-lying regions and retreating again with enormous force. These early tides did more than shape the planet's geography. They sculpted coastlines, eroding rock and depositing sediments that would one day become rich soils and mineral layers. They stirred the waters of the young oceans, mixing chemical compounds and distributing them across different regions. Where water met land, the tidal cycle created environments that were constantly shifting between wet and dry, providing the conditions for chemical reactions that might not have occurred otherwise. Over time, these processes played a crucial role in shaping the chemistry of the oceans, creating conditions that would one day nurture the first forms of life. The moon's gravitational influence also linked Earth and its satellite in a slow, delicate dance. As Earth's rotation slowed, the moon's orbit gradually expanded. It drifted farther away, and the tides became gentler. Even today, that process continues, with the moon moving a tiny distance away from Earth each year. Its pull is weaker now, but the fundamental effects it set in motion long ago still shape the planet's systems. The moon's influence reached into every layer of Earth's story. It steadied the tilt that controlled the seasons, slowed the spin that governed the rhythm of day and night, and stirred the oceans that would become the cradle of life. Its presence turned what could have been a chaotic, unstable world into a planet with regular patterns, predictable cycles, and the conditions necessary for complexity to grow. Above the planet's surface, it continued its silent orbit, indifferent to the changes below yet essential to every one of them. It did not create Earth's oceans or its atmosphere, but it shaped how they behaved. It did not make the seasons, but it gave them their steady rhythm. And though it was born from violence, the moon's quiet gravity brought balance to a restless world, weaving its influence into the very fabric of Earth's unfolding story. Beneath the young sky and its restless clouds, beneath the new oceans that had gathered in craters and valleys, the ground itself was struggling to find balance. Earth's surface was not yet the stable floor we walk upon today. It was a thin, fragile skin stretched over a restless interior, constantly torn apart and rebuilt by forces rising from below. Even as the planet's crust cooled and hardened, it was never truly at rest. At first, the crust was little more than a delicate shell, barely thick enough to hold itself together. Tremendous heat still surged upward from the interior, left over from the planet's violent birth and fueled by the slow decay of radioactive elements deep inside. This heat made the crust unstable. It cracked and split, allowing molten rock to surge upward in fiery outbursts that remade the surface again and again. In many places, the crust was pulled back into the interior, melting into magma and then rising once more to form new layers. No part of Earth's surface lasted for long. The earliest crust was different from the familiar continents and ocean floors of today. It was thinner and weaker, formed mostly from dense, dark basalt that erupted from the mantle below. As it cooled, this crust floated atop the molten interior like a fragile raft on a boiling sea. But the movement of heat beneath it was relentless. Vast plumes of magma pushed upward from deep within the planet, forcing the crust to bulge and crack. When parts of the surface cooled and grew heavy, they sank back into the depths, melting and mixing with the mantle once again. This constant cycle of creation and destruction kept the surface in motion. Over millions of years, this chaotic process gave rise to something new, the beginnings of plate tectonics. Driven by the slow churning of the mantle beneath, sections of the crust began to move in great slabs, colliding, separating, and sliding past one another. These slabs, known as tectonic plates, were massive, covering entire regions of the planet's surface. Their movements were slow, measured in centimeters per year, but over geological time, they reshaped the face of Earth. Where plates met, their collisions were violent. One slab would dive beneath another, sinking into the mantle in a process called subduction. The descending plate melted deep below, fueling volcanic eruptions that built towering mountains and vast chains of islands. In other places, plates pulled apart, and magma from below surged upward to fill the gap, creating new crust on the ocean floor. Where they slid past each other, the grinding motion built enormous stress that was released in sudden earthquakes. These shifting plates did more than shape the surface. They acted as a vast recycling system, breaking down and rebuilding Earth's crust in an endless cycle. Old crust was swallowed into the mantle and reborn as new volcanic rock. Mountains rose and were eroded by wind and rain, their minerals carried into rivers and oceans, where they were buried, melted, and thrust upward once more. Elements essential for life, such as carbon and phosphorus, were cycled between the deep earth, the surface, and the atmosphere. Without this constant movement, many of the chemical processes that sustain life today might never have occurred. Tectonic activity also played a critical role in shaping the continents themselves. Over time, lighter, less dense rock formed from repeated volcanic eruptions accumulated on the surface. This rock was more buoyant than the basaltic crust that made up the ocean floors, so it floated higher on the mantle and resisted being pulled back into the depths. Slowly, fragments of this lighter crust grew larger and thicker, merging into the first continental masses. These early continents drifted across the planet's surface, carried along by the movement of the plates beneath them. They collided and broke apart again and again, reshaping the geography of the world countless times over billions of years. The movement of the crust also shaped the climate. Volcanic eruptions released carbon dioxide and other gases into the atmosphere, warming the planet and influencing weather patterns. When mountains rose, they altered wind and rainfall, creating new environments and influencing where rivers and seas formed. The erosion of these mountains exposed fresh rock, which reacted with carbon dioxide and helped regulate the planet's temperature. Every shift and collision above had consequences that rippled through the oceans, the atmosphere, and even the chemistry of life itself. Deep within the planet, the mantle continued its slow, powerful convection, driving the plates and reshaping the crust above. The surface of Earth was never static, never finished. Continents moved like pieces on a vast, slow-moving puzzle. Ocean basins opened and closed, mountains rose where plates collided, then crumbled back into dust over eons. The crust's constant motion ensured that Earth remained a dynamic and ever-changing world. This restless nature set Earth apart from many of its planetary neighbors. Mars, with its thick, unmoving crust, grew cold and quiet long ago. Venus, with no global system of plate tectonics, remained locked in a cycle of surface renewal that erased much of its geological history. Earth, by contrast, evolved into a planet that remade itself again and again with a surface that recorded its long and complex story. The crust's refusal to stay still would shape everything that followed. It built mountains that altered weather and rivers that carved landscapes. It created continents that would one day cradle forests, deserts, and seas. And it wove a deep, continuous connection between the deep interior and the surface, ensuring that the story of Earth remained one of constant renewal. The Earth that faced the late heavy bombardment was no longer the chaotic sphere it had once been. Its crust had grown thicker and more stable, oceans had begun to spread across its surface, and its atmosphere was slowly settling into place. For the first time in its history, the planet seemed to be approaching something resembling balance, but that fragile stability was about to be shattered by one final and extraordinary event. This was not just another chapter of early planetary violence, it was a cosmic upheaval unlike anything before or since, and it would leave its mark on every terrestrial world in the solar system. Between roughly 4,100,000,000 and 3,800,000,000 years ago, the inner solar system was engulfed in a storm of impacts that scientists call the Late Heavy Bombardment. It was as if the calm that had begun to settle over the young planets was suddenly broken by a new wave of destruction. Asteroids and comets, some the size of mountains and others as large as small moons, were thrown inward from the cold outer reaches of the solar system. Their orbits became chaotic, their paths unpredictable. Earth, still young and geologically active, stood directly in their way. The reason for this surge of impacts is still the subject of debate. One leading theory suggests that the giant planets Jupiter and Saturn, in the process of shifting into their final orbits, disturbed vast regions of icy and rocky debris in the outer solar system. Their immense gravity scattered countless objects inward, sending them careening toward the inner planets. Another theory proposes that instead of a sudden spike in collisions, the bombardment was a slower, more drawn-out decline in impact frequency as the solar system gradually cleared itself of leftover debris. Scientists continue to debate which version is true, but whatever the cause, the effects were undeniable. A rain of destruction swept across the inner solar system, reshaping the worlds we know today. The evidence of this violent era still surrounds us. The moon's cratered surface is a fossil record of those ancient collisions. Mercury and Mars bear similar scars, their crusts pocked with enormous basins that formed during this time. On Earth, the story is harder to read. Plate tectonics, erosion, and volcanic activity have erased most direct traces of these impacts. Yet their signature remains hidden in the isotopic fingerprints of ancient minerals and in subtle chemical patterns preserved deep within the crust. What made the late heavy bombardment different from earlier collisions was not just the violence of individual impacts, but their sheer frequency and timing. The young planet had already begun to stabilize, and life's earliest chemical steps may have been underway. Then, suddenly, that progress was interrupted. Some of the impacting bodies were hundreds of kilometers wide, releasing unimaginable energy on impact. Oceans that had only recently formed were boiled away by the heat. Surface rocks melted, and vast quantities of atmosphere were blasted into space. For any early life that might have been emerging, these impacts would have been catastrophic, possibly sterilizing entire regions or even the whole surface. Yet even as they destroyed, these colossal collisions also delivered new materials that would become essential to the planet's future. Many of the bodies striking Earth contained water locked within minerals or frozen as ice, along with organic molecules forged in the cold darkness of space. These were not just random projectiles, they were carriers of chemical potential. Over millions of years, they replenished the planet's water reserves and enriched its surface with carbon based molecules that could serve as raw materials for life. The consequences of the bombardment were not limited to the delivery of new ingredients. The heat released by these impacts created conditions where chemistry could flourish. Around the edges of giant craters, hydrothermal systems formed as water percolated through the superheated crust. These environments were dynamic and reactive, rich in energy and minerals, and they may have provided ideal conditions for simple molecules to assemble into more complex structures. Some researchers believe these sites could have been the cradles of life itself, turning catastrophe into opportunity. The bombardment also influenced the deep interior of the planet. Immense impacts did not just scar the surface, they reached deep into the mantle, mixing and redistributing elements. This helped shape the planet's long term geochemical evolution and may have influenced volcanic activity and plate movements for billions of years to come. The Earth that emerged from this era was chemically richer and geologically more complex than the one that had entered it. Whether the late heavy bombardment was a sudden catastrophe or a prolonged decline remains uncertain, but by the time it ended, the solar system had been transformed. Most of the stray debris had been swept away, and the orbits of the planets had stabilized. The frequency of collisions dropped dramatically, and Earth finally entered a more peaceful chapter of its story. Although its scars have long since faded beneath oceans and continents, the legacy of the late heavy bombardment endures. It was a trial by fire and stone that tested the young planet to its limits. It boiled seas and stripped atmospheres, but it also brought water, organics, and energy. It may have delayed life's emergence, but it may also have provided the final ingredients needed for it to begin. In this paradox of destruction and creation, Earth was forever changed. The world that emerged from that final storm was stronger, more complex, and more prepared for the astonishing story that was still to come. The rains that had fallen for thousands of years had finally carved their way into the planet's surface. They gathered in the deep scars left by impacts, pooled in vast basins, and spread across the still forming crust. The Earth, once a world of fire and stone, was now wrapped in water. These early oceans were not like the ones we know today. They were dark and acidic, their surfaces shrouded in volcanic steam, their depths stirred by the heat rising from the young planet's restless interior. But within these waters, something remarkable was beginning to unfold. The new oceans were not just passive pools of water. They were immense chemical laboratories, filled with dissolved gases, minerals, and energy. Every drop carried the fingerprints of the planet's violent past. Volcanic eruptions spewed carbon dioxide, sulfur dioxide, methane, and ammonia into the air, and rain drew these gases down into the oceans. There, they dissolved and mixed, creating a chemical broth unlike anything that exists on Earth today. These reactions were not simple. They were complex networks of interactions driven by differences in temperature, pressure, and composition, constantly forming and breaking apart new compounds. Deep beneath the surface, where seawater met hot rock, hydrothermal vents spewed scalding plumes rich in minerals and metals. These vents were unlike anything on the modern seafloor. They were hotter, more volatile, and far more active, their chimneys coated in strange mineral layers that precipitated as the hot fluids met cold seawater. Around these vent systems, steep chemical gradients formed. The difference between the scorching, mineral-rich fluids and the cooler, oxygen-free seawater created natural energy sources capable of driving reactions that would otherwise be impossible. In these dynamic environments, molecules began to build upon one another. Simple carbon compounds formed spontaneously in the presence of heat and mineral catalysts. Some of these combined into more complex molecules, such as amino acids, the fundamental components of proteins. Others linked into simple sugars, essential for future forms of metabolism. Chains of carbon and hydrogen assembled into fatty molecules that could trap other compounds inside thin membranes, foreshadowing the boundaries that would one day define living cells. These reactions did not happen all at once, nor did they occur in a single location. They unfolded slowly and in many different places at once, each environment offering unique conditions. Along shorelines, tidal pools evaporated and refilled, concentrating molecules until they could react more easily. In deeper waters, minerals carried by underwater vents acted as natural catalysts, lowering the barriers for chemical transformations. Even lightning in the atmosphere, striking the gas-rich air above the seas, created reactive molecules that rained down into the water. The entire planet had become a vast, interconnected network of chemical experiments, all running simultaneously, all shaping the ingredients of life. The minerals delivered by meteorites during earlier bombardments also played a role. Iron, nickel, and other metals dissolved into the water, creating new reaction pathways. Some of these metals helped assemble long chains of molecules, while others acted as scaffolds, stabilizing fragile structures long enough for them to grow more complex. The constant mixing of materials from land, sky, and space created a chemical richness that no single environment could have achieved alone. Over time, the oceans became reservoirs of extraordinary potential. Countless types of molecules swirled through their depths, colliding, bonding, and breaking apart. Some combinations were fleeting, vanishing as quickly as they formed. Others lingered, building layer upon layer of complexity. The seas were not yet alive, but they were full of the ingredients that life would require. The difference between simple chemistry and the first primitive biology was narrowing. Even without cells, the oceans displayed behaviors that hinted at what was to come. Certain molecules could replicate themselves, using raw materials from their surroundings to make copies. Others began to organize into small, membrane-like bubbles, trapping energy and compounds inside. These tiny pockets created internal environments that were different from the water around them, allowing more complex reactions to occur. In time, these self-replicating systems and enclosed chemical structures would become central to life's machinery. The early oceans were also shaped by the planet's geology. As tectonic activity reshaped the seafloor, new vents opened and old ones closed, shifting the locations where chemistry thrived. Continents had not yet formed, but small patches of land occasionally rose above the surface, offering new sites for evaporation and concentration. The constant cycling of materials between ocean and crust ensured that the chemistry remained dynamic, never reaching a static equilibrium. The chemical story unfolding in these waters was not directed by any plan. It was the result of countless chance events, each governed by the laws of physics and chemistry. Yet together, these events created a system of astonishing complexity. In a planet that had once been nothing but molten rock and empty sky, molecules were beginning to organize themselves in ways that hinted at purpose. The line between non-living matter and living systems was still far away, but the first steps toward crossing it were already being taken. Within these vast, restless oceans, Earth's next great chapter was beginning to write itself. The waters that had fallen from alien skies and boiled from the planet's own depths had become more than a surface feature. They were now the stage upon which the first story of life would unfold, setting the foundation for everything that would one day swim, crawl, and think. For hundreds of millions of years, Earth had been a world of water and stone. Its surface shifted and cracked, its skies hissed with volcanic breath, and its oceans churned with chemical possibility. Yet, through all of this, one feature we now take for granted was still missing. There were no continents, there were no mountains or plains, no river valleys or plateaus. The entire face of the planet was dominated by restless seas and thin, dark crust that was constantly torn apart and remade by the planet's inner heat. But deep beneath the surface, slow changes were unfolding that would eventually give rise to the first dry land. It began with the movement of molten rock within Earth's interior. As the mantle churned and circulated, some regions melted more completely than others, producing magma that was lighter and richer in silica. When this buoyant material cooled and solidified, it formed a new kind of crust, thicker, less dense, and far more resistant to sinking back into the mantle. Unlike the heavy basalt that made up the ocean floor, this rock floated higher on Earth's surface, like a raft rising above the waves. These were the first proto-continents, small patches of granite crust that emerged above the seas like scattered islands. At first, these landmasses were small and scattered, more like archipelagos than continents. Many were no larger than modern volcanic islands, while others stretched for hundreds of kilometers before sinking beneath the weight of new lava or breaking apart under tectonic stress. The early Earth was still incredibly dynamic, and these patches of buoyant crust were constantly colliding, merging, and sometimes disappearing altogether. Yet over time, they grew larger and more stable, stitched together by volcanic eruptions and welded by the immense pressure of collisions. The rise of these proto-continents had profound consequences for the young planet. For the first time, there were surfaces that stood above the endless seas, exposed directly to the atmosphere and the forces of weather. Rain, which had once fallen only into the oceans, now struck rock. Wind swept across newly formed ridges. Temperature changes caused cracks and fractures to widen. These simple processes began to wear away the exposed rock, breaking it into grains of sand and dust. Rivers and streams, though primitive, carried this material back into the oceans, where it settled into layers on the seafloor. This cycle of erosion and sedimentation marked the beginning of a slow but powerful transformation. The interaction between land and water was more than just a physical reshaping of Earth's surface. It was a chemical revolution. As rainwater flowed over rocks, it dissolved minerals and carried them into the oceans. These dissolved elements changed the composition of seawater, altering its acidity and nutrient content. New types of sediments formed, rich in iron, silica, and other elements that would play crucial roles in future geological and biological processes. Volcanic activity added another layer of complexity. As magma erupted onto the surface, it built new land and deposited fresh minerals. Some of this material weathered quickly, feeding chemical reactions in the oceans. Other parts became part of the growing continents, creating thicker, more stable landmasses. Over millions of years, the interplay between volcanic construction and erosion sculpted the shape and character of the early continents, building landscapes that were rugged, barren, and alien. The newly formed shorelines were unlike anything we know today. They were jagged and unstable, constantly shifting as tectonic forces moved the underlying plates. Waves crashed against steep cliffs, eroding them grain by grain. In some places, lava continued to pour into the sea, creating new land almost as quickly as the old was worn away. In others, sediment built up into broad, shallow platforms, forming the first primitive continental shelves. These regions, where land and sea met and mingled, became some of the most chemically dynamic environments on the planet. The interaction between land and water also influenced the chemistry of the atmosphere. As minerals weathered and dissolved, they reacted with gases in the air, drawing down carbon dioxide and releasing other compounds. This helped regulate the planet's climate and created feedback loops that stabilized surface conditions. In this way, the rise of continents became part of Earth's broader environmental system, linking the deep interior, the surface, the oceans, and the sky in a single, interconnected web. With more land above the waterline, new habitats also emerged. Tide pools formed along rocky shores, concentrating water and chemicals in small, enclosed spaces. These environments may have provided ideal conditions for complex chemical reactions, perhaps even helping along the steps that would eventually lead to life. Mineral surfaces on land acted as natural catalysts, aligning and assembling molecules in ways that were less likely to occur in the open ocean. Even though no plants or animals yet existed to colonize them, these early continents were already influencing the future of biology. The story of Earth's first continents is one of slow emergence, constant change, and delicate balance. They were born from deep planetary forces, built grain by grain through erosion and uplift, and shaped by the unending conversation between water and rock. They did not yet resemble the great landmasses we know today, but they marked a turning point in the planet's evolution. For the first time, Earth was no longer a world defined only by fire and water. It was becoming a planet with land, a place where oceans met stone, and where the surface itself began to play an active role in shaping the future. From these humble beginnings, the continents would continue to grow and shift, forming the foundations of mountains, valleys, and plains. Their chemistry would shape the oceans, their weathering would sculpt the atmosphere, and their presence would make possible the diversity of landscapes that life would one day inhabit. The planet was entering a new phase of its story, one written not just in fire and fluid, but now also in stone. Long before the first living cell stirred in Earth's ancient seas, long before continents formed and skies turned blue, the planet's chemistry was already being written. But not all of it was born here. Much of what would make Earth a cradle for life arrived from far beyond its skies, carried by travelers that had been wandering the solar system and even the galaxy for billions of years. These messengers were comets and meteorites, the hidden architects of a world still finding its shape. The story begins in the distant outskirts of the solar system, in regions so cold and remote that sunlight is little more than a pale glow. There, vast clouds of ice and rock drift through space, remnants of the solar nebula that never coalesced into planets. Many of these icy bodies were rich in water, carbon, and simple organic molecules formed in the frigid dark. Occasionally, their quiet orbits were disturbed. A gravitational nudge from a passing star or the pull of a massive planet could fling them inward, sending them on long journeys toward the heart of the solar system. When these ancient wanderers crossed paths with Earth, the results were dramatic. Some burned up in fiery streaks across the sky, disintegrating in the upper atmosphere. Others survived the plunge and struck the surface with tremendous force, delivering their cargo directly into the young planet's environment. With each impact, they deposited water locked in ice, along with a host of carbon-based molecules, including amino acids, the basic building blocks of proteins. The evidence for this cosmic delivery is written in the isotopes of Earth's water. By studying the ratio of hydrogen to deuterium, Scientists have discovered that much of Earth's water matches the signature found in certain types of comets and carbonaceous chondrites, a class of primitive meteorites. This suggests that a significant portion of the water now filling Earth's oceans was not originally part of the planet at all. It was carried here, grain by grain, droplet by droplet, by countless collisions over millions of years. These impacts did more than bring water. They enriched the planet with a wide range of organic molecules that Earth's own chemistry might never have produced so readily. Laboratory studies have shown that amino acids and other prebiotic compounds can form naturally in the cold vacuum of space, assembled on dust grains or within the icy mantles of comets. Once delivered to Earth, these molecules entered the oceans, where they mixed with chemicals already forming from volcanic activity and hydrothermal vents. Together, they created a far richer chemical landscape than Earth could have achieved alone. Some meteorites that have fallen to Earth even today still contain these ancient molecules, preserved almost unchanged since the birth of the solar system. The Murchison meteorite, which landed in Australia in 1969, contains over 70 different amino acids, many of which are rare or absent on Earth. This remarkable sample shows that the cosmos is capable of producing complex chemistry long before planets even exist, and that this chemistry is widespread. It hints that the seeds of life are not confined to one world, but are scattered across the galaxy, waiting for the right conditions to take root. The delivery of extraterrestrial material was not a single event, but an ongoing process. During the late heavy bombardment, countless comets and asteroids continued to strike Earth, further enriching its oceans and crust. Some impacts likely vaporized large amounts of water and organics, but over time, the balance tipped toward accumulation. As the bombardment slowed and the planet stabilized, the chemical inventory of Earth became increasingly diverse and complex, laying the groundwork for the next great transition. The importance of these cosmic gifts cannot be overstated. Without them, Earth might have remained a dry, barren world, its chemistry too simple to spark the intricate reactions needed for life. Instead, the combined forces of planetary geology and cosmic delivery created an environment brimming with possibility. Water, once locked in distant ice, now flowed across the planet's surface. Carbon compounds, formed in the darkness between the stars, now dissolved in Earth's seas. Amino acids, shaped in the cold of interstellar space, now drifted in the same waters that would one day cradle life. It is humbling to realize that the recipe for life was not written solely on Earth. It was drafted in supernovae that forged the elements, refined in the icy hearts of comets, and delivered by meteorites older than the planet itself. In a sense, Earth was seeded by the universe, its potential enriched by countless fragments from beyond. Each grain of dust and shard of rock that struck the surface carried within it a piece of a larger story, a story that began long before Earth existed. As the planet continued to cool and evolve, the materials brought by these ancient messengers mixed and reacted with those formed on Earth itself. Together, they created a chemical stage unlike any other, one capable of producing the first self-replicating molecules. The architecture of life was not built in isolation. It was a collaboration between a young world and the cosmos that surrounded it, a shared effort that turned a barren planet into a place where biology could eventually flourish. The hidden architects of Earth's story were not sculptors of stone or builders of mountains. They were fragments of ancient worlds, travelers from distant regions of space, and carriers of the raw materials from which life would emerge. Their work was subtle, patient, and profound, shaping not just the chemistry of a planet, but the destiny of everything that would one day live upon it. The earth that rotated beneath the faint glow of the young sun bore little resemblance to the planet we know today. The skies were heavy and thick, stained in hues no modern eye has ever seen. The air itself was not the crisp mixture of oxygen and nitrogen we breathe now, but a suffocating brew of gases that would kill almost any living thing alive today. Methane swirled with carbon dioxide, clouds of ammonia mingled with nitrogen, and traces of sulfur compounds drifted from the countless volcanoes that still scarred the surface. There was no oxygen yet, no ozone to shield the surface from ultraviolet light. It was a world wrapped in poison, and yet it was precisely this poison that made everything that followed possible. The faint young sun shone with only about 70% of the power it does today, a star still growing into its strength. By all accounts, Earth should have been a frozen wasteland under such weak light. But this dense, greenhouse-rich atmosphere trapped heat like a vast thermal blanket, wrapping the planet in warmth and preventing its young oceans from freezing solid. Carbon dioxide was especially important in this balance. Volcanoes were constantly pumping it into the air, and with no plants or weathering processes to draw it back down into the crust, it built up over time. Methane, produced by chemical reactions deep within the earth, and perhaps even by early microbial life later on, added even more insulation, amplifying the greenhouse effect. This delicate balance between sunlight and greenhouse gases created a climate stable enough for liquid water to remain on the surface. Without it, the oceans that had formed from relentless rain might have turned to global ice, halting the chemistry that was slowly stirring beneath their waves. Instead, the atmosphere, toxic though it was, held the planet in a narrow window where water could flow, storms could form, and rivers could carve their paths into the raw, young crust. But the early atmosphere did more than just hold in heat. Bathed in relentless ultraviolet radiation from the sun, its gases were constantly being torn apart and recombined high above the surface. These reactions created new molecules, some of them far more complex than the simple gases that formed them. Methane could break apart and form long chains of hydrocarbons. Nitrogen and hydrogen, split by solar radiation, could form nitriles and amines. Even traces of water vapor contributed, breaking apart into reactive fragments that helped drive further chemistry. These reactions filled the upper atmosphere with a haze of organic particles. Much of this material eventually drifted downward, settling into the oceans below like a gentle rain of invisible dust. It was not alive, but it was rich with potential. The molecules formed in the sky joined those delivered by meteorites and those forming near hydrothermal vents on the seafloor, adding yet another layer of chemical diversity to the young planet's inventory. In this way, the atmosphere acted as both a shield and a workshop, protecting the planet from freezing while also crafting new ingredients for the chemistry of life. On the surface, the oceans themselves were alien to anything we would recognize today. They were dark and acidic, tinted by dissolved iron and other minerals leached from the crust. Into these waters fell the products of the atmospheric reactions, molecules that might cling together and react again under the influence of lightning, ultraviolet light, or simple chance. Over time, some of these molecules could form more elaborate structures, chains of carbon and hydrogen, rings of nitrogen and oxygen, or even small polymers capable of storing chemical information. The interaction between the poisonous skies and the restless oceans was not static. As volcanic activity waxed and waned, the balance of gases in the atmosphere shifted. Methane levels might rise with increased volcanic outgassing, thickening the greenhouse blanket. Ammonia, released from deep within the earth, could react with sunlight and vanish, replaced by nitrogen. Each change altered the chemical reactions taking place above and below, continually reshaping the environment in which prebiotic chemistry was unfolding. Even the planet's early magnetic field, which had begun to form deep within its molten core, played a subtle role. By deflecting much of the solar wind, it helped preserve the atmosphere from being stripped away entirely. Without that invisible shield, the delicate chemical balance that sustained liquid water and drove organic synthesis might never have been possible. The atmosphere was not a static layer of gas, but a dynamic, evolving system that worked in concert with the planet's interior and oceans. It captured the faint warmth of a young star, shielded the surface from deadly radiation, and supplied an endless rain of organic molecules to the waters below. It was harsh and deadly to anything resembling modern life, but it was also fertile ground for the slow, intricate steps that would one day lead to biology. This poisonous cloak, so different from the breathable air we know, was a crucial stage in Earth's transformation. It turned a barren world into a chemical laboratory where energy from the sun, elements from the crust, and molecules from space all converged to build complexity from simplicity. Every breath we take today traces its lineage back to that early, alien sky when life's first ingredients were forged not in gentle sunlight and fresh air, but in a world wrapped in poison. As the poisonous skies continued to churn above the young Earth, and the oceans below grew richer with chemical possibilities, a new and quieter process began to unfold. It was not sudden like the violent impacts that had once scarred the planet, nor dramatic like the torrential rains that carved its surface. It was slow and patient, unfolding over millions of years, yet it would become one of the most important forces shaping Earth's destiny. This was the birth of a self-regulating system, a natural balance between rock, water, air, and fire, one that would keep the planet's climate within the narrow limits where life could exist. It began with rain. The same clouds that once poured water over molten plains now carried another power. They could strip gases from the air. Every drop that fell from the young sky dissolved a small amount of carbon dioxide, one of the most abundant greenhouse gases in the atmosphere. When that rain reached the ground, it interacted with minerals in the rocks, forming weak acids that reacted with the surface. Over time, these chemical reactions transformed the carbon dioxide into stable compounds like bicarbonates, which were carried by rivers into the oceans. There, they eventually settled to the seafloor as solid carbonates, locking the carbon away inside rocks that would remain buried for millions of years. This was the beginning of a vast planetary cycle. The atmosphere no longer existed in isolation above the world, and the crust beneath it was no longer a passive foundation. They were now linked, part of a feedback system that would act like a planetary thermostat. When the climate grew warmer and rainfall increased, more carbon dioxide was drawn out of the air, reducing the greenhouse effect and cooling the planet. When the world cooled and rainfall slowed, less carbon dioxide was removed, allowing it to build up again and trap more heat. But the system did not stop there. Deep within the Earth, heat and pressure continued to drive volcanic activity, just as they had since the planet's earliest days. Magma rising from the mantle released vast amounts of carbon dioxide and water vapor into the air, replenishing the gases that weathering and rainfall had removed. This ongoing exchange between the deep interior and the surface maintained the balance. The more the atmosphere cooled and thinned, the more volcanic activity could rebuild it. The more it thickened and warmed, the more rainfall could draw it down again. This push and pull created a dynamic stability. The climate no longer swung wildly between extremes as it once might have. Instead, It began to hover within a range that allowed liquid water to persist, even as the young sun remained fainter than it is today. Without this self regulating feedback, the early Earth could easily have frozen into a lifeless snowball or overheated into a runaway greenhouse. Instead, the surface temperature settled into a delicate equilibrium, warm enough for oceans to remain liquid, but cool enough for weathering to continue. The effects of this balance rippled through the entire planetary system. As carbonates formed and sank into the ocean floor, they carried with them not only carbon, but also calcium and other elements. These sediments built thick layers of rock that would, over time, be buried, melted, and recycled by plate tectonics. When these rocks were pushed deep into the mantle and heated, they could release their trapped carbon back into the atmosphere through volcanic eruptions. This slow recycling of carbon from air to rock to magma and back again became one of the most fundamental cycles on Earth. The balance was not perfect, nor was it immediate. It operated over timescales far longer than any storm or eruption. A single volcanic event could inject vast amounts of carbon dioxide into the atmosphere within days, while weathering might take hundreds of thousands of years to draw it down again. Yet, over millions and even billions of years, the two forces averaged out, creating a planetary environment that remained stable enough for life to emerge and evolve. The interplay between land and sky also had subtle effects on ocean chemistry. As rivers carried dissolved minerals and bicarbonates into the seas, they helped control the acidity of the water, influencing the types of chemical reactions that could take place there. This, in turn, shaped the conditions under which the first organic molecules could form and interact. The oceans were not just a passive container for life's building blocks. They were active participants in a larger planetary system driven by the carbon cycle. Even the continents themselves played a role. As they grew and eroded, they exposed new minerals to weathering, drawing down more carbon dioxide. Their shapes influenced rainfall patterns, which affected how quickly carbon could be removed from the air. Mountains that rose through tectonic collisions increased erosion, while vast lowlands slowed it. In this way, geology, climate, and chemistry became deeply intertwined, each shaping the other over immense spans of time. This great balancing act would prove to be one of Earth's most remarkable features. It transformed a volatile, unpredictable world into one capable of maintaining stability over billions of years. It allowed the planet to adapt to changes in the sun's brightness, the shifting positions of continents, and even the rise of life itself, which would one day alter the carbon cycle in ways no geology alone could. With every rainfall and volcanic plume, with every grain of rock that weathered into clay, Earth refined its natural thermostat. It was not a machine, but a living, breathing system of feedbacks and responses, endlessly adjusting to keep the world within the bounds where water could flow and chemistry could flourish. And in this quiet, persistent dance between the air, the land, and the deep interior, the stage was set for everything that would follow. Earth's story had always been one of turmoil, but by this point, the chaos was softening into something else. The fires that once engulfed the planet's surface were mostly extinguished beneath thickening crust. The endless rain of space debris had slowed to a trickle. Oceans that had once boiled away now remained, stretching across the planet's face in vast, glimmering expanses. For the first time since its formation, Earth was not simply surviving its own creation, it was beginning to hold steady, and that steadiness changed everything. One of the most important shifts was the permanence of liquid water. It had taken unimaginable spans of time for the surface to cool enough for water to condense and stay. It had taken even longer for those early oceans to endure the fiery assaults of bombardment and the fury of planetary heat. But now, those waters were here to stay. They pooled in basins carved by ancient impacts and filled broad plains where the crust had stretched and thinned. They did not vanish when the sun rose or disappear when the winds shifted. They persisted, covering much of the surface in a layer that reflected sunlight and softened the planet's temperature swings. The stability of water was matched by the growing stability of Earth's climate. Greenhouse gases released from deep within the planet trapped enough warmth to keep the oceans from freezing, even though the young sun was fainter than it is today. At the same time, chemical weathering on land and in the oceans helped remove carbon dioxide from the atmosphere, preventing runaway heating. Together, these opposing forces balanced one another, maintaining a climate mild enough for liquid water to remain stable over millions of years. It was a delicate equilibrium, but it held. Time itself became a powerful ally. In earlier ages, sudden catastrophes had wiped the slate clean again and again. Impact after impact had boiled oceans, stripped atmospheres, and melted crust. Now, those interruptions were rare. Instead of destruction, resetting the clock every few thousand years, processes could unfold over millions. Molecules that formed in one place were no longer instantly obliterated. They could drift, mix, and linger. They could accumulate in lakes, tide pools, or deep sea basins. They could meet other molecules and form new compounds, some more complex and more stable than those that came before. The oceans turned into immense chemical laboratories. Minerals dissolved from rocks on land enriched the water with phosphorus, iron, and trace metals. Temperature differences between the deep sea and the sunlit surface created gentle circulation patterns, distributing nutrients and energy throughout the water column. Sunlight reached shallow seas, driving reactions that assembled carbon and hydrogen into more elaborate molecules. Lightning storms delivered bursts of energy to the atmosphere, forging reactive compounds that eventually rained down into the seas below. What mattered most now was not a single dramatic event, but the quiet accumulation of opportunity. Organic molecules that had once been rare and fleeting were now common, swirling through the waters and clinging to mineral surfaces. Some formed short chains, others folded into shapes that could interact with their surroundings. Many broke apart and reformed in endless cycles. Most of these reactions led nowhere, but some, given time and stability, built complexity upon complexity. The surface of the planet offered its own variety of environments. Shallow tidal flats were exposed to cycles of drying and wetting as the moon's pull created regular rhythms in the rising and falling seas. Each cycle concentrated organic material, sometimes exposing it to ultraviolet light from the sun, which could split bonds and rearrange atoms into new configurations. Inland, volcanic plains with pools fed by hot springs provided a different kind of chemistry, with minerals precipitating out of solution and capturing molecules in their lattices. Even within the same environment, conditions fluctuated just enough to test countless chemical possibilities without erasing them entirely. Above, the atmosphere added yet another layer of complexity. Ultraviolet radiation continued to split molecules apart in the upper layers, creating reactive fragments that recombined into new compounds. These products fell back to Earth, raining into the oceans or settling on land. They joined the molecular dance already unfolding there, adding new participants to an ever-growing chemical conversation. What was most remarkable about this era was not a single reaction or a single location. It was the persistence of conditions that allowed complexity to build rather than vanish. Earth no longer lurched from one catastrophe to the next. Its oceans did not disappear. Its surface was not regularly remade. Its climate did not swing wildly from one extreme to another. Instead, it offered patience millions upon millions of years, during which chance and chemistry could slowly weave intricate patterns out of simple beginnings. By this time, Earth was still lifeless, but it was no longer sterile. Its oceans were filled with organic molecules of every shape and size. Its surface and atmosphere were rich with chemical diversity, and everywhere the stage was set for what would come next. There was water to mix and dissolve. There was energy from sunlight, lightning, and the planet's interior. There was time, far more than ever before, for improbable events to unfold and build upon themselves. The planet had reached a new threshold. It was no longer just habitable in theory. It was a stable, nurturing cradle where chemistry could linger and evolve. And in that long stretch of calm, in the quiet patience of a world finally ready, the first faint steps toward life were beginning to stir. Long before forests shaded the land or animals swam through the seas, long before even plants or shells existed, something extraordinary was already happening on Earth. It was happening quietly, almost invisibly, hidden beneath the waves of ancient oceans and tucked away in the smallest corners of the planet. The world that had once been nothing but molten rock and poisonous skies was now stable enough to host liquid water, moderate temperatures, and an abundance of chemical ingredients, and somewhere within that delicate balance, life began. It did not appear with fanfare or sudden transformation. There were no footprints pressed into the mud, no shapes that an untrained eye could see. The first life on Earth existed on a scale far smaller than anything visible, and it moved through its environment not with legs or fins, but with chemistry. Scientists believe this remarkable transition from non-living molecules to living systems happened around 3,800,000,000 years ago, though perhaps even earlier. At that time, Earth was still a strange and unfamiliar planet. Continents were only beginning to form, and the atmosphere remained rich in gases that would be deadly to us today. Yet, within the darkness of those early oceans, something stirred. The earliest evidence of this hidden transformation is preserved in rocks far older than almost anything else on the planet. In ancient formations found in places like Greenland and Western Australia, geologists have discovered chemical signatures that hint at biological activity. Ratios of certain isotopes of carbon, for example, appear skewed in a way that suggests they were shaped by living processes. These subtle chemical traces are like fingerprints left behind by organisms too small and too delicate to fossilize, yet their presence is unmistakable. They are the echoes of life's earliest experiments. In slightly younger rocks, the evidence becomes clearer. Among the most striking are stromatolites, layered structures formed by colonies of tiny microorganisms, most likely cyanobacteria, that lived in shallow waters. As these microbes grew, they trapped and bound sediments, building up thin layers over time that hardened into stone. The result was a series of dome-shaped structures that rose slowly from the seafloor, sometimes reaching meters in height over thousands of years. These ancient microbial mats were not only signs of life, but also builders of ecosystems, creating new habitats and altering their environment in subtle but important ways. Alongside stromatolites, scientists have discovered microfossils that provide direct glimpses into the appearance of Earth's earliest life forms. These microscopic remains, preserved in rock layers more than 3,400,000,000 years old, are shaped like tiny filaments, spheres, or tubes. They likely belong to simple single-celled organisms that lived by harnessing chemical energy from their surroundings. Some may have consumed iron or sulfur, while others may have used light to drive their metabolism. Whatever their methods, these early microbes left behind the first physical evidence of life's existence on the planet. Life's emergence did not transform Earth overnight. It spread slowly, adapting to the conditions of a still hostile world. Many of these early organisms lived in extreme environments, clinging to the mineral-rich edges of hydrothermal vents or thriving in the thin layers of water beneath the surface crust. These were places where energy and nutrients were abundant and where ultraviolet radiation from the sun could not reach to destroy fragile molecules. In such protected niches, life refined itself, evolving new strategies for survival and reproduction. The impact of these early organisms, though invisible on a human timescale, was profound. As they grew and multiplied, they began to influence their surroundings in subtle ways. Microbes that used sunlight for energy, for example, released oxygen as a byproduct, though at first it was quickly absorbed by minerals in the oceans and crust. Over immense spans of time, however, their activity would reshape the chemistry of the entire planet. The rise of oxygen in Earth's atmosphere, which would eventually pave the way for more complex forms of life, began with these silent pioneers. The story of life's origins is still incomplete, and many mysteries remain. Scientists do not yet know the exact moment when the first true cells formed, nor do they fully understand the sequence of steps that led from simple organic molecules to self-replicating organisms. But the evidence that life was present as early as 3,800,000,000 years ago is now overwhelming. It reveals a truth as humbling as it is astonishing. Life did not require a perfect world. It began in one that was hot, toxic, and constantly changing, and it found a way to endure. Even today, the traces of those ancient pioneers can still be found in the rocks beneath our feet and in the genes of every living creature. The chemistry they mastered billions of years ago still powers the cells in our bodies. The patterns of growth they followed still guide ecosystems across the planet. And the quiet persistence they embodied remains one of the defining qualities of life itself. What began as microscopic whispers in a barren sea would, in time, give rise to forests, animals, and civilizations. But at the dawn of it all, life's story was written in the smallest of footprints, etched into stone by organisms too tiny to see and too ancient to imagine. It was a story that began not with noise or spectacle, but with quiet persistence, unfolding molecule by molecule in a world that had only just learned how to live. For hundreds of millions of years after life first appeared, Earth remained a microbial world. The planet was still a quiet place, inhabited only by single-celled organisms clinging to rocks, floating in the seas, or thriving in the mineral-rich waters around hydrothermal vents. The oceans were dark and murky, filled with dissolved metals and gases, and the skies above were still devoid of oxygen. Yet deep within this seemingly unremarkable world, something profound was beginning to unfold. A new biological process was taking shape, one that would transform not only the chemistry of the oceans, but also the destiny of the planet itself. This process was photosynthesis. Somewhere in the shallows of ancient seas, some microbes evolved the remarkable ability to harness light from the sun to power their metabolism. Using sunlight as an energy source, they could split molecules of water and use carbon dioxide from the atmosphere to build sugars, releasing oxygen as a byproduct. It was a small biochemical innovation, but it changed everything. For the first time, life could directly tap into the vast and steady stream of energy pouring from the sun, turning it into chemical fuel. At first, The oxygen produced by these microscopic pioneers never accumulated in the air. The oceans were rich in dissolved iron and other reactive minerals, and every atom of oxygen that was released immediately found something to bind with. It reacted with iron in the water, forming rust-like compounds that settled to the seafloor in layers of reddish-brown sediment. These deposits, known today as banded iron formations, stretch for kilometers across ancient continental shelves and provide a striking record of this invisible revolution. Over time, they built up into thick, alternating bands of iron-rich rock, painting the ocean floor with the first chemical signature of a changing world. This transformation of the oceans was not a quick one. It unfolded slowly, over tens and hundreds of millions of years, as photosynthetic microbes multiplied and spread. The oxygen they produced continued to react with iron until the supply was finally depleted. When that happened, oxygen began to react with other elements, oxidizing sulfur, manganese, and a host of trace metals. The chemistry of seawater was shifting in fundamental ways, and with it, the conditions for life itself. The changes did not stop beneath the waves. As more oxygen was produced than could be consumed by reactions in the water, some of it began to escape into the atmosphere. At first, the amounts were tiny, far too low to support any kind of complex organism, but over immense spans of time, oxygen levels slowly rose. It reacted with gases like methane and ammonia, altering the greenhouse properties of the air and affecting the planet's climate. It also began to form ozone high in the atmosphere, creating a protective shield against ultraviolet radiation. This thin layer of gas would one day make it possible for life to move onto land, though that was still far in the future. Meanwhile, the impact of photosynthesis rippled through the biosphere itself. The ability to use sunlight as an energy source gave organisms an enormous evolutionary advantage. They no longer had to rely solely on chemical reactions around vents or the breakdown of organic matter. Energy was no longer scarce or localized. With sunlight available across the surface of the planet, life could spread into new environments and grow in abundance. This expansion created new ecological pressures, new opportunities for competition, and new paths for evolution to explore. The oxygen released by these early organisms also paved the way for entirely new forms of metabolism. Some microbes learned to use oxygen to extract far more energy from their food than was possible before. This innovation, known as aerobic respiration, would become the foundation for nearly all complex life that followed. But even before multicellular organisms appeared, the presence of oxygen allowed for greater diversity and complexity among single-celled life. As the oceans cleared and the chemistry of the planet shifted, the stage was being set for everything that would follow. The rocks of the seafloor, once dull and dark, now glowed with streaks of rust-red iron. The skies, once thick with methane and carbon dioxide, began to hold traces of a new and reactive gas. And the surface waters, once home to a sparse scattering of microbes, now teemed with photosynthetic life, capturing sunlight and shaping the planet's future. The rise of photosynthesis did more than produce oxygen. It rewrote the rules of the planet's chemistry, creating new pathways for elements to cycle through the environment. It changed the composition of the oceans, the structure of the atmosphere, and the flow of energy through ecosystems. It linked the biosphere to the geology and climate of the planet in ways that would continue to evolve for billions of years. All of this began with tiny cells no larger than a speck of dust, drifting in ancient seas and capturing light from a distant star. Their work was slow and relentless, yet its consequences were vast. With each pulse of oxygen released into the water, with each atom of iron rusted on the seafloor, they were laying the foundation for a living planet. They were creating a blueprint for a biosphere, one that would one day support forests and animals, coral reefs and civilizations. But in those distant ages, it was still a quiet revolution, written in the language of sunlight and water, molecule by molecule, across a world that was slowly learning how to breathe. For billions of years, the air that wrapped around Earth was utterly unlike the one we know today. It was heavy with carbon dioxide, methane, ammonia, and nitrogen, with barely a trace of oxygen. The skies were hazy, tinged in shades of orange and green, and the planet beneath them was dominated by microbes that thrived in oxygen-free environments. Yet deep within the oceans, the slow and steady work of photosynthetic life had been quietly changing everything. For ages, the oxygen produced by these tiny organisms never built up in the air. It was swallowed by chemical reactions almost as quickly as it formed, rusting iron on the ocean floor, oxidizing volcanic gases, and binding to countless elements dissolved in water. But as time went on, the planet's chemistry began to shift. Iron in the oceans was eventually used up, and the other sinks for oxygen grew saturated. At last, oxygen could no longer be hidden away in the rocks and minerals of the earth. It began to escape into the atmosphere. What followed was one of the most dramatic and far-reaching transformations in the planet's history. This event, which scientists call the Great Oxidation Event, unfolded around 2,400,000,000 years ago. It did not happen overnight. It was a slow and relentless shift, measured not in centuries or millennia, but in tens of millions of years. Yet its consequences were immense. Oxygen, once a rare trace gas, became a significant part of the atmosphere. It rose from virtually nothing to perhaps 1 or 2% of the air, and eventually far higher. This change marked a turning point not only for the atmosphere, but for life itself. Oxygen is a highly reactive gas, and its presence reshaped the chemistry of the planet's surface and oceans. Many of the microbes that had flourished in the Old World found themselves poisoned by the new gas and vanished into isolated environments where oxygen was scarce. But for others, oxygen offered an extraordinary opportunity. Organisms that evolved to use it for respiration discovered a far more efficient way to extract energy from food. With more energy available, they could grow larger, become more complex, and adapt to a wider range of environments. The stage was being set for a future in which multicellular life would eventually flourish. The rising oxygen also triggered changes high above the surface, where it played an unexpected role in shaping Earth's destiny. In the upper layers of the atmosphere, ultraviolet light from the sun split some oxygen molecules into individual atoms. These atoms recombined into a new form of oxygen known as ozone. Unlike ordinary oxygen, ozone is extremely effective at absorbing ultraviolet radiation, which can damage or destroy delicate biological molecules. Over time, a thin but powerful layer of ozone formed in the stratosphere, creating a shield that softened the sun's most dangerous rays before they could reach the surface. This invisible barrier was more than just protection. It allowed life to venture closer to the surface, where sunlight was stronger and energy was more abundant. In the oceans, it enabled organisms to inhabit shallower waters without being destroyed by radiation. Much later, it would make it possible for life to leave the seas altogether and colonize the land. Without ozone, every exposed surface would have been bathed in lethal radiation, and the evolution of complex life would likely have been impossible. The transformation of the atmosphere also altered the face of the planet in ways that could be seen as well as felt. As methane levels declined and oxygen levels rose, the haze that had once wrapped the Earth in a diffuse, reddish glow began to clear. Sunlight reached the surface more directly, and the color of the sky shifted. The pale orange dome that had once hung above the planet turned blue, scattered by nitrogen and oxygen molecules in the air. The view of the heavens, once filtered and dim, grew brighter and clearer, revealing the sun and stars with new clarity. With more oxygen in the air, weathering processes on land accelerated, breaking down rocks and releasing minerals into the oceans. This influx of nutrients fueled the growth of microbial life, which in turn produced more oxygen, creating a self-reinforcing cycle. The planet was not just evolving biologically, but geochemically. Air, water, rock, and life were now deeply intertwined, each shaping the others in ways that would continue for billions of years. This transformation was not without upheaval. As methane, a powerful greenhouse gas, declined, global temperatures may have dropped dramatically. Some scientists believe that this shift helped trigger one of the earliest ice ages, coating much of the planet in ice. Yet even this apparent setback became part of Earth's evolving story. Life adapted, persisted, and continued to shape the atmosphere with each passing generation. By the time oxygen had become a permanent feature of the air, the planet was no longer the same place. The oceans were clearer, the skies were brighter, and the surface was bathed in a new spectrum of light. The shield of ozone protected the fragile chemistry of life, and oxygen itself powered new forms of metabolism that would eventually lead to greater complexity. What had begun as a byproduct of microscopic life had reshaped the entire world. The Earth that emerged from this transformation was more than just habitable. It was prepared for the next chapters of its story, where complexity would flourish and diversity would explode. The planet had been reborn, its atmosphere no longer a shroud of toxic gases, but a life-giving envelope, rich with potential and ready for what was still to come. Beneath the thin shell of air and water, Earth was never still. Even when the surface seemed calm and unchanging, the ground beneath it was quietly shifting. The plates, still drifting as they had for billions of years, continued their slow migration across the face of the planet. Over spans of time far longer than any life could witness, this movement transformed Earth's surface again and again, shaping its geography, climate, and the very story of life itself. Continents were not fixed features, they were travelers, gathering into vast supercontinents and then breaking apart to wander the globe once more. This slow rhythm, repeated many times in Earth's history, was among the most powerful forces shaping the planet's evolution. Each supercontinent began as scattered fragments that collided and fused into immense landmasses. They endured for hundreds of millions of years before the forces beneath them eventually tore them apart. Then, the fragments drifted away, only to collide again in new configurations. It was a grand cycle that never truly ended. The consequences of these shifts rippled through every part of the planet's system. When continents merged into supercontinents, the vast interiors of those landmasses often became dry and inhospitable, cut off from the moderating influence of the oceans. Enormous deserts spread across their centers, and temperature extremes grew sharper. Meanwhile, the clustering of land near the equator created expansive tropical zones where heat and sunlight fueled intense weather patterns and abundant rainfall. These climatic changes shaped the environments in which life evolved, influencing where ecosystems could thrive and where they could not. The formation of supercontinents also redirected the flow of the oceans. As landmasses converged, they altered the shape and size of ocean basins, changing the pathways of currents that transported heat and nutrients around the planet. This, in turn, affected global climate. Warm waters carried toward the poles could melt ice sheets and raise sea levels, while cold currents flowing toward the equator could cool entire regions and trigger glacial periods. The dance of the continents was deeply entwined with the rhythm of ice ages and warm eras, creating cycles of climate change that would echo through Earth's history. Their breakup brought its own transformations. When supercontinents split apart, new coastlines appeared, stretching thousands of kilometers across the globe. These shallow coastal zones, where sunlight could easily penetrate and nutrients were abundant, became cradles of biodiversity. Life flourished in these regions, and new species evolved to fill the ecological opportunities they created. As land masses drifted apart, populations of organisms were isolated from one another. In their separation, they followed different evolutionary paths, giving rise to the astonishing diversity of life that would one day populate the planet. The movement of continents also influenced the chemistry of the atmosphere and oceans. The collision of plates could raise towering mountain ranges, and the weathering of those mountains pulled carbon dioxide from the air, cooling the planet. The splitting of continents often unleashed vast volcanic eruptions along new rift zones, releasing gases that warmed the climate and altered ocean chemistry. Each tectonic shift had consequences that reached far beyond geology, touching the cycles of carbon, oxygen, and nutrients that sustained the biosphere. Some of the most dramatic episodes in Earth's history were directly linked to these continental movements. When land masses collided, the stress and heat sometimes triggered immense volcanic outpourings, known as large igneous provinces. These eruptions released enormous amounts of greenhouse gases, disrupting global climate and contributing to mass extinctions. Yet even these catastrophes created new opportunities for life. Once the environment stabilized, ecosystems rebounded, often with entirely new forms of life adapted to the transformed world. The arrangement of continents could even decide the character of entire eras. When land was clustered near the poles, ice sheets grew and global temperatures dropped. When it was concentrated in the tropics, weathering increased, drawing down greenhouse gases and altering atmospheric composition. The location of mountain chains guided wind patterns and rainfall, shaping where forests could grow and where deserts would dominate. Ocean gateways opened and closed as continents shifted, connecting or isolating marine environments and influencing the migration of species. The interplay between geology and life was not a one-way street. As life spread across the continents, it began to influence the very forces that shaped them. Plants accelerated the weathering of rocks, altering the carbon cycle and changing the climate in ways that affected continental movement. Microbes contributed to the formation of soils and sediments that were later drawn into the mantle through subduction, subtly influencing the chemistry of magmas and volcanic gases. Over time, the living world and the moving earth became inseparable, each shaping the other's evolution. These changes unfolded so slowly that no single species could witness them from start to finish. A supercontinent might assemble over 300 million years, only to break apart over another 200 million. Oceans opened and closed, mountains rose and wore away. Continents drifted from equator to pole and back again. Yet each motion set the stage for profound transformations, reshaping environments and guiding the course of evolution. The continents did not simply move. They orchestrated the conditions of life. Their collisions created mountains that redirected wind and rain. Their separations sculpted coastlines where biodiversity could bloom. Their positions decided the strength of ocean currents and the timing of ice ages, and through it all, they served as the shifting canvas upon which Earth painted its biological story. The dance of the continents continues even now. They move too slowly for us to feel, but their influence is everywhere in the distribution of climates, the shapes of ecosystems, and the paths life has taken. Over billions of years, this ceaseless motion has transformed the planet into a dynamic, ever changing world. It is a dance that has no final step, and it is still unfolding beneath our feet. The story of Earth is not a straight path from chaos to calm. It is a rhythm, a pulse, a long and winding journey marked by moments of stillness and moments of upheaval. Even as continents drifted and oceans deepened, even as life grew more complex and the atmosphere filled with oxygen, the planet's history was shaped by recurring cycles of catastrophe and renewal. Across billions of years, Earth has fallen into deep, frozen sleeps and awoken into bursts of transformation. Life has flourished, vanished, and returned again and again in a pattern that defines the very heartbeat of the planet. One of the most dramatic examples of this rhythm is found in the great mass extinctions that have punctuated Earth's history. These were not ordinary events. They were global resets, moments when vast numbers of species vanished in geologically brief periods of time. Some were triggered by explosive volcanic eruptions that filled the skies with ash and choked the atmosphere with greenhouse gases. Others followed sudden shifts in climate or the impact of asteroids from space. Whatever their cause, they reshaped the tree of life, pruning entire branches and leaving space for new ones to grow. The earliest known extinction events occurred long before animals walked the land or plants covered the continents. In those ancient oceans, where microbial life had dominated for billions of years, environmental changes could be devastating. Fluctuations in oxygen levels, shifts in ocean chemistry, or changes in nutrient supply could wipe out vast populations of microorganisms. Each crisis erased much of what existed, yet each also cleared the way for new forms to emerge, better suited to the changing world. Perhaps the most dramatic interruptions in Earth's history came when the planet itself seemed to fall asleep beneath a blanket of ice. These global glaciations, known as snowball Earth events, may have covered the planet from pole to equator in sheets of frozen water. Oceans froze over, reflecting sunlight back into space and deepening the cold. Life survived only in isolated pockets, clinging to existence beneath the ice or near hydrothermal vents on the seafloor. For millions of years, Earth lay silent under its icy shell, a frozen world adrift in space. Yet even the deepest freezes were temporary. Over time, volcanic activity released carbon dioxide into the atmosphere, trapping more heat and eventually melting the ice. When the world thawed, it did not return to the way it had been. The release of meltwater, the influx of nutrients, and the changes in ocean circulation triggered bursts of biological activity. In the wake of these global winters came explosive evolutionary radiations, periods when life diversified rapidly and filled new ecological spaces. The planet's most famous extinction events came much later, when life had grown complex and ecosystems rich. Roughly 450 million years ago, during the Ordovician period, a sharp drop in global temperatures caused glaciers to spread and sea levels to fall, wiping out many marine species. Around 250 million years ago, a catastrophe known as the Permian extinction destroyed nearly all life in the oceans and most on land, possibly triggered by massive volcanic eruptions in what is now Siberia. And 66 million years ago, an asteroid impact ended the age of dinosaurs, clearing the stage for mammals to rise. Each of these events devastated life, but each also set the conditions for new evolutionary chapters to unfold. These cycles of destruction and renewal reveal both the resilience and the fragility of life. On one hand, they show how easily the balance of the planet can be disrupted, how a shift in temperature, a burst of volcanic gas, or a single impact from space can unravel ecosystems built over millions of years. On the other hand, they show how persistent life can be, finding ways to endure even in the harshest conditions and seizing new opportunities when the world changes. Earth itself participates in this rhythm. The same forces that fuel its geological activity, that drive the drift of continents and the rise of mountains, also contribute to its moments of crisis. Volcanism shapes the atmosphere, influencing climate and triggering extinctions. Tectonic shifts alter ocean currents and weather patterns, setting the stage for global ice ages. Even impacts from beyond the planet are part of the cosmic environment Earth inhabits. These events are not interruptions in the planet's story. They are integral to it, part of the ongoing dialogue between the Earth and the universe around it. From the perspective of a human lifetime, such events seem almost unimaginable in their scale and violence. But on the time scale of the planet, they are part of a natural cycle, a pulse that has repeated again and again for billions of years. Life rises, falls, and rises again. The earth freezes and thaws, grows barren and blooms once more. Each crisis reshapes the world, and each recovery builds upon what came before, adding new layers of complexity and diversity. The history of Earth is written not just in steady progress, but in these dramatic swings between silence and resurgence. It is a story of pauses and accelerations, of sudden endings and unexpected beginnings. The planet's long sleep and sudden awakenings have defined its character, guiding the course of evolution and shaping the landscapes and ecosystems that exist today. And somewhere in that great rhythm, life has always found a way to continue, adapting to the planet's changing heartbeat and writing the next chapter of its story. The world beneath our feet is far less peaceful than it appears. Mountains rise so slowly that they seem eternal. Rivers carve their valleys over spans of time too long for us to grasp, and continents appear rooted firmly in place. Yet this calm surface is a thin veil over something far more dynamic. Deep below, the same forces that once tore the newborn Earth into shape are still alive. They have not faded or vanished with time. They continue to sculpt the planet day by day, writing new chapters in a story that began more than 4 billion years ago. The violence of Earth's birth never truly ended, it simply changed form. The colossal collisions that once built continents have become the slow shoving of plates that still rearrange the land. The fiery seas of molten rock that once covered the surface now emerge in concentrated bursts from volcanoes. The pressure that once fractured the crust during the planet's formation is still stored in the rocks, waiting to be released in the sudden jolt of an earthquake. The energy has not gone away. It only hides beneath our feet, reshaping the world in ways both dramatic and subtle. Every volcanic eruption is a direct continuation of that ancient energy. When molten rock from deep inside the planet breaks through to the surface, it is the same internal heat that once melted entire oceans of stone. Volcanoes continue to build new land, forming islands in the open sea and mountains on continents. Along the mid-ocean ridges, magma rises to create new crust, pushing older crust outward and renewing the ocean floor in an ongoing cycle of creation and destruction. In places like Iceland and Hawaii, chains of volcanoes rise above the waves, fed by plumes of heat that travel upward from deep within the mantle. These fiery outbursts are more than spectacular displays of nature's power. They are visible reminders that Earth is still evolving. Earthquakes, too, are echoes of the planet's restless past. They occur when immense stress builds up along faults, where the planet's rigid outer shell grinds and slips. In an instant, that stored energy is released, sending waves rippling through the crust. Some earthquakes reshape landscapes on a massive scale, lifting entire sections of land or lowering them beneath the sea. Others redirect rivers, split valleys, or trigger landslides that alter the terrain forever. Even when they last only seconds, they reveal a truth written deep into Earth's story. The ground beneath us is never truly still. Some of the most dramatic signs of this ongoing transformation can be found where continents collide. When the Indian subcontinent pushed into Eurasia tens of millions of years ago, it did not stop. It still presses forward today, lifting the Himalayas ever higher and pushing the Tibetan Plateau farther upward into the sky. Similar collisions are happening all around the globe, building new mountain ranges that will stand for ages before erosion grinds them back down. These towering formations are monuments to slow, unstoppable motion, driven by the same energy that once shaped Earth's continents from chaos. Even the creation of islands is part of this continuing legacy. Far from the edges of tectonic plates, mantle plumes rise like columns of heat from deep within the planet. When they break through the crust, they build volcanic peaks that emerge above the ocean's surface. The Hawaiian Islands are one such example, formed as a plate, slowly drifted over a stationary plume. Over millions of years, new volcanoes rose while older ones sank back into the sea, leaving a trail of islands that map the motion of the plate itself. These volcanic chains tell a story written in stone, one that links the planet's fiery origins to its living surface. The fingerprints of ancient energy extend beyond landforms. Deep within the ocean, volcanic activity fuels hydrothermal vents that spew mineral-rich water into the dark abyss. These vents create oases of life in an otherwise barren landscape, proving that Earth's internal heat continues to shape not only the surface, but also the ecosystems that depend on it. Even the atmosphere and climate feel the influence of this buried power. Large volcanic eruptions can inject ash and gases into the air, blocking sunlight and cooling the planet for years. Others release greenhouse gases that trap heat, influencing climate patterns over thousands of years. The results of these ongoing processes are visible everywhere. New crust forms along spreading ridges, while old crust is swallowed back into the mantle at subduction zones. Earthquakes reshape coastlines and fracture mountains. Volcanoes build islands and bury landscapes under layers of fresh rock. Over millions of years, entire continents drift across the globe, colliding and breaking apart as they have done since the beginning. Each of these events is a chapter in the same ancient story, driven by forces as old as the planet itself. What we see around us is not a finished product. It is a planet still in motion, still alive with the energy of its creation. The calm landscapes and familiar horizons we know today are fleeting moments in a process that will continue long after us. Mountains will crumble and rise again. Oceans will open and close. Islands will emerge from the sea and disappear beneath the waves. Every tremor, eruption, and shifting plate is a whisper from Earth's deep past, a reminder that the same forces that shape the world we stand on are still at work. The Earth's birth was violent, and its legacy endures. It lives on in the pulse of volcanoes, the jolt of earthquakes, and the slow drift of continents. It shapes the air, the water, and the land, weaving together the conditions that sustain life. Our planet is not a relic of its fiery beginnings. It is a living, changing world, still sculpted by the energy that first gave it form. The story of Earth began with heat and violence, with molten oceans and skies filled with fire. Yet somewhere in the vast gulf of time, that same world of stone and storm transformed into something capable of asking questions about itself. The journey from raw chemistry to conscious thought was not quick, nor was it inevitable. It was the result of billions of small changes, each building upon the last, until the planet that once boiled with magma was home to beings who could look up at the stars and wonder where they came from. For most of Earth's history, life was invisible to the naked eye. The first organisms were tiny and simple, little more than self-replicating molecules wrapped in fragile membranes. They fed on chemical gradients at the edges of hydrothermal vents or captured energy from sunlight in shallow seas. They did not think or plan, but they changed their environment simply by living. Through photosynthesis, they filled the atmosphere with oxygen. Through respiration, they returned carbon to the air. They were small, but they were powerful, reshaping the chemistry of oceans and sky and making new possibilities for what life could become. Over time, some of these simple cells began to cooperate. They merged with one another, forming more complex structures. Some cells became specialists, handling energy production, while others focused on reproduction or movement. This cooperation gave rise to the first eukaryotic cells, which contained internal compartments and could perform many tasks at once. With complexity came diversity, and life began to explore new forms and strategies. The leap from single-celled organisms to multicellular life was another quiet revolution. At first, simple colonies formed, groups of cells sticking together after division. Gradually, these colonies became more organized. Cells began to communicate, dividing labor between them. Some became part of a body's surface, others formed tissues to carry nutrients or signals. These experiments in cooperation laid the groundwork for the first plants, fungi, and animals. The oceans, once ruled by microbes alone, filled with strange new creatures. Soft-bodied forms filtered nutrients from the water. Worm-like animals burrowed through sediments, mixing and oxygenating the seafloor. Later, hard shells and skeletons evolved, offering protection and structure. The Cambrian explosion, a burst of evolutionary innovation more than 500 million years ago, filled the seas with predators and prey, swimmers and crawlers, hunters and filter feeders. Life was no longer a hidden chemistry beneath the waves. It had become a force that carved niches and shaped ecosystems. Plants crept onto land, harnessing sunlight to build forests that transformed the atmosphere. Animals followed, adapting lungs for air, limbs for movement, and senses for new environments. Insects took to the skies. Amphibians gave rise to reptiles, which in turn spawned the great age of dinosaurs. Mammals scurried in the shadows, waiting for their chance. Each branch of the tree of life pushed outward, exploring new possibilities, driven by the same simple laws of mutation, selection, and survival that had guided life from its earliest days. Intelligence did not appear suddenly. It began as awareness, a sensitivity to light, sound, and movement. Nervous systems evolved to process information and coordinate responses. Brains grew larger and more complex, capable of storing memories and learning from experience. Some animals began to use tools to solve problems, to communicate with signals more sophisticated than instinct alone. Over millions of years, these incremental changes gave rise to minds capable of planning, creativity, and curiosity. In one branch of the mammalian lineage, these capacities grew especially powerful. Early primates developed grasping hands, forward-facing eyes, and social behaviors that rewarded cooperation and communication. Their descendants learned to shape stones into tools, to control fire, to hunt in coordinated groups. They painted symbols on cave walls and buried their dead with care. In them, the universe was beginning to reflect on itself. Eventually, humans emerged, beings capable not only of surviving but of imagining. They built languages to share knowledge across generations, stories to make sense of the unknown, and technologies to reshape the world around them. They studied the stars, split atoms, and mapped the structure of life itself. They created art, music, and mathematics, all expressions of minds that had grown from the simplest beginnings. This transformation, from molten planet to thinking species, is one of nature's most astonishing achievements. The iron that once sank to Earth's core now carries oxygen through our blood. The carbon that once drifted through space as stardust now builds the neurons that form our thoughts. The energy that once roared in volcanic eruptions now fuels the electric signals that flash in the human brain when we dream. Even now, that journey continues. Life is still evolving, still adapting to new challenges, still exploring new possibilities. Intelligence itself may yet take forms we cannot imagine, shaped by forces we do not yet understand. The story is not finished. It is still unfolding, written by the same deep processes that once melted rocks, raised continents, and filled the oceans. From fire to thought, from chaos to consciousness, Earth has transformed itself into something more than a planet. It has become a vessel for awareness, a place where the universe has learned to look inward and ask questions. And all of it began with the same violent energy that once forged a world from dust and flame. For all the chaos and violence that shaped Earth's early history, there is a quiet truth beneath it all. Our world should not exist as it does. It is the result of a long chain of improbable circumstances, a series of coincidences so delicate that even the smallest difference could have meant a lifeless rock instead of a living planet. Every feature that makes Earth what it is today had to align just right, and together they form a cosmic puzzle that, so far, we have not seen repeated anywhere else in the universe. The first piece of that puzzle is size. Earth is neither too large nor too small. If it were much smaller, like Mars, it would have cooled too quickly, losing its internal heat and the geological activity that recycles elements through its crust and atmosphere. A smaller planet would also struggle to hold onto a thick atmosphere, its weaker gravity allowing vital gases to drift into space. Without an atmosphere, there would be no protection from radiation, no stable climate, and no liquid water on the surface. If Earth were much larger, gravity would be stronger, possibly trapping a suffocating blanket of hydrogen and helium like the gas giants. That would have created a very different kind of world, hostile to the chemistry of life as we know it. Earth's size is a balance point, just heavy enough to hold the right kind of air, and just active enough inside to keep its surface alive. Where Earth orbits in the solar system is another crucial part of the story. It sits in what scientists call the habitable zone, the narrow band of distance from the Sun, where temperatures allow water to remain liquid. Move our planet slightly closer to the Sun, and the oceans might have evaporated long ago, creating a runaway greenhouse effect like the one that transformed Venus into a world of acid clouds and crushing heat. Place Earth a little farther away, and it might have frozen solid, its surface locked beneath layers of ice, like the moons of Jupiter and Saturn. Even within this habitable zone, the planet's slightly elliptical orbit ensures that seasonal changes are gentle rather than extreme, giving life a stable environment in which to grow and evolve. Another stroke of luck is hidden deep within Earth itself. The planet's metallic core generates a powerful magnetic field that extends far into space, forming a protective bubble around the atmosphere. Without this magnetic shield, the solar wind would strip away the gases that make our planet breathable, just as it did on Mars. It would also bombard the surface with high energy particles, making conditions far harsher for life. This magnetic field is not guaranteed. It requires a liquid outer core, a solid inner core, and a balance of heat and motion that stirs the metals within. All of these conditions had to align, and they have continued to work together for billions of years, shielding Earth from the worst of space's hostility. Then there is the Moon, Earth's silent companion. It, too, is the product of an unlikely event, a colossal collision with a planet-sized body that reshaped both worlds. The Moon stabilizes Earth's axial tilt, preventing wild swings that could send climates lurching from ice ages to infernos. It slows the planet's rotation, lengthening the days and creating a rhythm that influences everything from weather patterns to biological cycles. Its tides stir the oceans, mixing nutrients and shaping coastlines where early life may have thrived. Without the Moon, Earth might still have been a habitable planet, but it would almost certainly have been a less stable one. Even the chemistry of Earth's crust and atmosphere is a delicate balance. The right mix of carbon, nitrogen, oxygen, and trace elements allows for a dynamic climate that neither freezes solid nor burns too hot. Volcanoes recycle gases from the deep interior, while weathering locks carbon away in rocks, creating a thermostat that has kept the planet's temperature within a narrow range for billions of years. Too much carbon dioxide, and Earth might resemble Venus. Too little, and the oceans would freeze. The balance is so fine that a small shift could have pushed the planet past the point where life could ever gain a foothold. Beyond these planetary features, the solar system itself plays a role. The presence of massive gas giants like Jupiter and Saturn helps protect Earth from frequent catastrophic impacts by deflecting many comets and asteroids. The Sun's stable output of energy provides a consistent source of warmth and light. Even the galaxy's structure matters. Our solar system orbits in a relatively calm region, far from the deadly radiation near the galactic core. Each of these factors alone would not have been enough. Together, they create the rarest of environments, a stable, temperate, and chemically rich world where liquid water can flow and complex molecules can assemble. It is a razor-thin balance, one that could easily have tipped in another direction, and yet, against the odds, it held. The more we search the cosmos, the more remarkable this alignment appears. Telescopes have revealed thousands of planets orbiting distant stars, yet none so far have mirrored Earth's perfect mix of size, orbit, atmosphere, magnetism, and companionship. Perhaps there are others, hidden in the vastness of space, waiting to be discovered. Or perhaps our world is as rare as it seems, a singular oasis born from an improbable sequence of events. Whatever the truth, Earth's uniqueness is a reminder of how finely tuned the conditions for life really are. From its molten heart to its distant orbit, from the pull of its moon to the shield of its magnetic field, everything had to fall into place. And because it did, a once molten sphere of rock and metal became something extraordinary, a living planet adrift in a cosmic sea. If you look at the Earth around you, you might think of it as something solid and permanent, a planet whose age-old stones have always been here, but almost everything on its surface has been recycled many times. Mountains have risen and crumbled, oceans have dried and filled again, continents have drifted and split apart. The skin of the planet is restless, and that means most of its earliest history has been erased. Yet, hidden deep within the crust, tiny relics from that lost time still remain. They are not monuments or fossils. They are far smaller, more delicate, and more revealing. They are minerals, scattered like time capsules across the ancient landscape, and they whisper stories from the day our world began. One of the most important of these storytellers is a small crystal called zircon. Zircons form when molten rock cools and solidifies, trapping inside them tiny traces of the environment in which they formed. Most minerals break down over time, but zircon is incredibly resilient. It resists heat, pressure, and erosion. Some zircons found on Earth are over 4 billion years old. They are older than any rock, older than any mountain, older even than the oldest known continents. In their atomic structure, they hold chemical fingerprints from a time when the planet was still in its infancy. Scientists study the isotopes within these crystals to reconstruct conditions on the early Earth. Isotopes are versions of the same element that contain different numbers of neutrons. Their ratios change predictably over time through radioactive decay, providing a kind of internal clock. By measuring these ratios, researchers can calculate when the crystal formed. More importantly, they can learn what the world was like at that time. Some zircons, for example, show evidence that liquid water existed more than 4 billion years ago, suggesting that oceans formed far earlier than once thought. Others record temperatures and pressures that hint at the presence of continental crust, implying that the first fragments of land rose above the seas while the planet was still very young. Zircons are not the only witnesses. Buried beneath layers of younger rock, deep geological formations also hold echoes of Earth's earliest days. These ancient rocks, known as cratons, are the stable cores of continents. They have survived for billions of years, enduring the movements of tectonic plates and the violence of volcanic eruptions. By drilling into them and studying their composition, scientists can piece together how the planet's crust evolved. The minerals and elements within these rocks carry signatures of the chemical processes that shaped Earth's surface and interior long before life appeared. Some clues are even older than the planet itself. Tiny grains of stardust, preserved inside meteorites that have fallen to Earth, predate the formation of the solar system. These ancient particles contain isotopic patterns that formed inside dying stars. By comparing them with materials found in Earth's oldest rocks, scientists can trace how cosmic debris contributed to the planet's composition. These connections reveal that our world was not created in isolation. It was built from the remnants of stars that lived and died long before the sun began to shine. To uncover these stories, scientists use a variety of tools and techniques. Mass spectrometers measure the isotopic makeup of tiny mineral grains with extraordinary precision. Electron microscopes reveal textures and structures smaller than a human hair. Geochemical models simulate the conditions under which these materials formed. By combining these methods, researchers can reconstruct events that occurred more than 4 billion years ago, long before any surface feature we see today existed. Even the mantle, the vast layer of rock beneath the crust, carries memories from Earth's earliest chapters. When volcanic eruptions bring pieces of the mantle to the surface, they often contain inclusions that formed deep inside the planet billions of years ago. These inclusions reveal details about the temperature, composition, and dynamics of the early mantle, offering insights into how Earth's interior evolved over time. They help scientists understand how the core separated from the mantle and how the magnetic field first emerged. Together, these traces form a scattered but powerful record. They are the pages of a book that has been mostly lost to erosion, subduction, and time. Each zircon crystal, each ancient rock, each grain of cosmic dust is a fragment of that missing story. When combined, they allow scientists to glimpse the world as it once was, when continents were just beginning to form, when oceans were still young, and when the sky was filled with debris from a chaotic solar system. The Earth has forgotten much of its earliest past, but it has not forgotten everything. Deep beneath our feet, and hidden within the smallest of minerals, the memory of the planet's first days still lingers, waiting to be read by those who know how to look. It is a story not written in words, but in atoms, isotopes, and ancient stone, a story that began before there were seas, before there was life, before there was even a name for the world beneath our feet. It is easy to think of Earth's birth as something that happened long ago, a fiery event sealed away in the past, but that image is incomplete. The truth is that Earth's creation has never really stopped. The same cosmic forces that built the planet from dust and stone are still shaping it now. They move continents, stir the deep interior, change the air we breathe, and sculpt the landscapes beneath our feet. The birth of Earth is not a finished chapter but a continuing story, one that unfolds moment by moment even as we live upon its surface. The continents, which seem so solid and unchanging, are in constant motion. They drift at the pace of a few centimeters each year, creeping across the surface like slow-moving rafts on a molten sea. Oceans open and close over spans of tens of millions of years. Mountain ranges rise as landmasses collide, only to be worn down by wind and rain until they vanish into plains. Even coastlines, which feel permanent on a human timescale, are always shifting as sea levels rise and fall, carving new boundaries where land and water meet. Every map ever drawn is a temporary snapshot, destined to become outdated as Earth's crust continues its slow, patient rearrangement. The magnetic field that shields the planet is another reminder that nothing here is fixed. Generated by swirling liquid iron deep within Earth's core, this invisible field protects the atmosphere from solar wind and cosmic radiation. But it is far from steady. The magnetic poles wander unpredictably, drifting dozens of kilometers every year. At irregular intervals, the field weakens and flips entirely, swapping north and south in an event that can take thousands of years to complete. These reversals have happened hundreds of times throughout Earth's history, and they will happen again. Even the planet's most fundamental shield is in constant motion, a living expression of the forces that continue to shape the world from within. The atmosphere, too, is always changing. Long before humans appeared, volcanic eruptions sent carbon dioxide and water vapor into the air, while ancient oceans pulled gases back down into their depths. Today, the balance is shifting once again. Human industry releases greenhouse gases faster than natural systems can absorb them, altering the climate and influencing global weather patterns. At the same time, volcanic events still reshape the air on shorter timescales. A single eruption can cool the planet by casting reflective particles high into the atmosphere or warm it by injecting greenhouse gases. The sky above us is a living system, constantly adjusting to the planet's internal rhythms and to the actions of the life that now covers its surface. Even the surface beneath our feet bears the marks of ongoing creation. Earthquakes ripple through the crust as tectonic plates grind past one another. New islands rise from the seafloor when underwater volcanoes erupt. Mantle plumes burn their way upward, forming volcanic chains that grow taller with each passing century. Rivers carve new valleys. Glaciers scrape deep scars into the land, and deserts expand or contract with shifting climates. The landscapes we inhabit are not permanent backdrops, but active participants in a story that continues to unfold. This constant motion extends beyond geology and climate. Life itself is part of the planet's ongoing transformation. As ecosystems adapt to changing conditions, they shape the surface in return. Coral reefs build massive limestone structures that alter coastlines. Forests capture carbon and release oxygen, influencing atmospheric chemistry. Microbes living deep underground participate in chemical cycles that affect the composition of rocks and minerals. Even humanity has become a geological force, altering river systems, moving mountains, and redistributing minerals across the globe. The actions of life, like the movement of continents or the flow of magma, are now woven into the planet's evolving story. The interconnectedness of these changes is profound. The drifting continents guide ocean currents that regulate climate. The shifting magnetic field shields the evolving atmosphere, which in turn shapes the surface below. Volcanic eruptions feed the atmosphere with gases that influence rainfall, which sculpts the land and nourishes ecosystems. Every part of Earth is linked to every other, forming a dynamic system that is always in motion. The birth of the planet was not a single event, but a continuous process that binds the deep past to the unfolding present. When we look at the world around us, we are not seeing a finished planet. We are witnessing a work in progress. The continents beneath our feet are still drifting. The magnetic poles above us are still wandering. The air we breathe is still evolving. The landscapes we know are still being carved, eroded, and remade. Even the life that thrives here, including our own, is part of the planet's ongoing transformation. Earth is still being born. It is a living, changing world, shaped by the same cosmic forces that formed it from dust and fire billions of years ago. That birth did not end with the cooling of the crust or the rise of the oceans. It continues today in every earthquake and eruption, in every shifting current of air and water, and in every adaptation of life. Our planet is a story still being written, a creation that never stops, and a reminder that the universe itself is not static, but always becoming something new. Every step you take, every breath you draw, is part of a story that began long before there were mountains, oceans, or skies. It is a story written not in ink or words, but in fire and stone, shaped by collisions so ancient that they belong to a time before time had meaning. The atoms that make up your bones, your blood, and the air in your lungs were forged in stars that died before our sun was born. Their ashes drifted through space, gathered into clouds, and were pulled together by gravity's quiet persistence until a world began to take shape. That world is still beneath your feet. It has been here all along, changing, evolving, and carrying you with it. The rocks beneath the soil are pages in this story. Each layer holds the memory of a chapter, a lava flow that once glowed brighter than any sunlit day, a seabed that teemed with the first microscopic life, a desert that stretched across a supercontinent now long gone. These stones remember things that no eye ever saw. They record the breath of ancient volcanoes, the footprints of vanished creatures, the fall of meteorites that once lit the sky with fire. They are the planet's memory, carved not by language but by time. And within those layers is a truth so profound that it reshapes how we see ourselves. The Earth's story is not separate from ours. It is ours. The iron in our blood once burned at the heart of stars. The calcium in our bones was born in the violent death of suns. The oxygen we breathe is the gift of ancient microbes that transformed the atmosphere long before humans walked the surface. The water that fills our cells fell from alien rocks and rained from the skies in a storm that lasted thousands of years. We are not visitors here. We are not outsiders looking in. We are the earth, thinking and dreaming about itself. Every force that shaped the planet still moves within us. The same gravity that pulled dust into worlds holds us to the ground. The same cycles that balanced ancient climates shape the seasons we live by. The same tectonic energy that pushed continents apart once created the minerals in our tools and the mountains we climb. We are not separate from these forces. We are born from them, carried by them, and dependent on them. When you look at a mountain range, you are looking at the frozen crest of a collision that began before mammals existed. When you touch a piece of granite, you are feeling the slow, patient work of molten rock rising from the depths of the mantle. When you listen to the crash of waves, you are hearing the legacy of tides set in motion by a moon that was once part of the earth itself. Every part of the world around you, from the clouds above to the core deep below, is part of the same unfolding story. And the story is not over. It will.